Some nights the sky holds a kind of stillness that feels almost deliberate, as though the darkness itself has leaned in just slightly to listen. If this feels like a good place to rest tonight, you're welcome to stay. Now, let's drift. There is something out there, not a crisis, not a catastrophe, just a quiet, persistent puzzle. A number. A small disagreement between two very careful measurements of the same thing. And somehow that number has become one of the most unsettling problems in all of modern science. Not because it is frightening, but because no one, not a single physicist or cosmologist or theorist anywhere on Earth can fully explain it. We'll get there gently, but first imagine standing outside on a clear night somewhere far from city lights. The kind of place where the stars don't just appear, they accumulate. Layer after layer of them, like a memory you didn't know you had. You breathe in, the air is cool, and somewhere above you, so far away that the distance is almost meaningless to the human mind, light is travelling. Light that left its source before your grandmother was born, before her grandmother was born, before anyone alive today drew their first breath. That light is still moving. It has been moving for millions of years, some of it for billions, and it will continue long after every human concern has quieted. There is something almost comforting in that if you let yourself feel it. The universe does not rush. It expands slowly and steadily in every direction at once. Every galaxy pulling away from every other galaxy, not because something is pushing them apart, but because the space between them, the fabric of reality itself, is gently, continuously growing. This is not a theory. It is one of the most well-confirmed observations in the history of science, and for most of the 20th century it seemed like something we understood. The story of that understanding begins with a man named Edwin Hubble. In the 1920s, working with a large telescope in the mountains above Los Angeles, Hubble made a discovery that permanently changed the way human beings understand their place in the cosmos. He noticed something in the light coming from a distant galaxies, a shift, a subtle stretching of the wavelengths toward the red end of the spectrum. Astronomers call this redshift, and what it means in its simplest form is movement. The galaxies were moving away, not just a few of them, all of them, in every direction. The further away a galaxy was, the faster it appeared to be receding. The universe, Hubble concluded, was not static. It was not the fixed eternal backdrop that most people had assumed. It was expanding. And if you ran the expansion backward in time, like rewinding a slow film, everything, all the matter, all the energy, all the space converged toward a single point, a single moment, what we now call the Big Bang. This was and remains one of the most profound realizations in human intellectual history. Not dramatic in the cinematic sense, but quietly segregating the way certain truths are the kind that settle into you slowly over years. What Hubble also gave us was a number, a rate. Researchers named it the Hubble constant, and it describes how fast the universe is expanding, specifically how much faster a galaxy moves away from us for every additional unit of distance between us. It is expressed in a unit that sounds almost poetic in its specificity, kilometers per second per megaparsec, a megaparsec being roughly 3.25 million light years. For decades, scientists worked to pin this number down. It turned out to be harder than expected. Different methods of measurement gave slightly different answers. But as instruments improve and techniques refine, the discrepancies were expected to resolve. The measurements everyone assumed would eventually converge on a single clean value. They did not. Here is where the quiet strangeness begins. There are two primary ways to measure the expansion rate of the universe, and they're both very good methods backed by decades of painstaking observation and cross-checking. The first uses a particular kind of star, a variable star called a Cepheid, whose brightness pulses in a rhythm that reveals its true luminosity. By comparing how bright it appears from Earth to how bright it actually is, scientists can calculate the precise distance to that star and from there to its galaxy. These distance measurements combined with the redshift of that galaxy's light give a value for the expansion rate. That value comes out to roughly 73 kilometers per second per megaparsec. The second method goes further back in time all the way to the earliest moments of the universe. About 380,000 years after the Big Bang, the universe had cooled enough for light to travel freely through space for the first time. That first light is still detectable today as a faint warmth across the entire sky, a kind of cosmic afterglow called the cosmic microwave background. By studying the precise patterns in that ancient light, scientists can reconstruct the conditions of the early universe, and from those conditions calculate what the expansion rate should be today. That value comes out to roughly 67 kilometers per second per megaparsec, 7367. 6 units apart, that gap sounds small, and it might be tempting to assume it is a measurement error, a rounding imprecision, something that a better telescope or a more careful analysis will eventually resolve. Researchers have been hoping that for more than a decade now. The measurements have grown more precise, more carefully verified, more independently confirmed, and the gap has not closed. It has held. Cosmologists have given this problem a name. They call it the Hubble tension. And the word tension is well chosen because that is exactly what it feels like. Two pieces of knowledge, each internally consistent and well supported, pulling against each other across a small but stubborn distance. It seems that the universe we can see is expanding faster than the universe's own origins predict it should be. The history of the cosmos as written in that ancient light does not quite match the cosmos as it behaves today. There is something missing, something that happened, or something that exists, or something about the fundamental nature of space and time that our current understanding has not yet accounted for. Scientists are still exploring what that something might be. One possibility, and it is explored with genuine seriousness, is that the universe contains a form of energy we do not yet fully understand. Something that has been influencing the expansion of the universe over time. Perhaps it has changed since the early universe. Perhaps what we measure today is not what existed then. If the energy driving cosmic expansion has shifted even slightly over the 13.8 billion year history of the universe, it would be enough to produce exactly the kind of disagreement we observe. There are other possibilities too. Some researchers have suggested there may be new particles, new physics, new layers of reality, operating at scales we have not yet probed. Not because they want there to be scientists are by nature resistant to unnecessarily complicating a model that already works well, but because the numbers keep asking for something more. What researchers have found again and again when they return to this problem is not reassurance. The tension is real, it is reproducible, it has survived many attempts to explain it away and it remains. There is something strangely peaceful in that, if you hold it lightly, the universe has a problem, a genuine, unresolved, beautiful problem. Not a catastrophe waiting to unfold, nothing about this changes the stars above you tonight, or the weight of the blanket, or the rhythm of your own breathing. It is a problem at the level of mathematics and light and deep time. A small disagreement measured across billions of light years, and it has not been solved. The people who spend their careers thinking about nothing else still do not know. The most advanced instruments ever built have weighed in and the answer has not yet arrived. There is something almost reassuring about that, not because the uncertainty is comfortable, but because it is honest. The universe is not finished teaching us. There is still more to understand than we have understood. And on a night like this, with the sky holding its particular silence that feels less like a problem than a kind of permission to not know, to rest inside the question rather than push toward an answer that isn't there yet. The stars above you tonight, the ones you can see and the billions you cannot, are all moving. Right now, in this moment, the galaxies at the edge of the observable universe are receding from us faster than light itself can travel. Not because they are rushing, but because the space between us and them is growing, expanding, opening the way a room might seem to expand when you fully relax into it. The universe is very large and it is getting larger. And the precise rate at which it is doing so is at this moment a question without a complete answer. And somehow that is enough to sit with tonight. The question doesn't need you to solve it. It's been there for billions of years, drifting through the dark, patient and unhurried, much like the night itself. And what scientists discovered next in trying to understand what fills that space between everything is something that has no colour, no temperature, no face, and yet makes up most of everything that exists. There is a particular kind of light that arrives already old. By the time starlight reaches your eyes on a clear night, the star that made it may have shifted position, dimmed, or in some cases ceased to exist entirely. What you are seeing is not the star as it is. You are seeing the star as it was sometimes thousands of years ago, sometimes millions. The night sky in this way is less a window and more a kind of museum, every point of light a preserved moment held in transit, still travelling towards something it may never know is watching. Edwin Hubble understood this, and it was precisely this quality of light, its faithfulness in carrying information across impossible distances, that allowed him to do what no human being had done before him. He wasn't looking for a revolution. Most revolutions in science begin that way, not with dramatic ambition, but with careful attention to something small. In Hubble's case, it was a faint smear of light in the constellation Andromeda. A nebula, astronomers called it at the time. A cloud of gas perhaps within our own galaxy. Something unremarkable, something filed away in catalogues without much ceremony. But Hubble, working at the Mount Wilson Observatory in California in the early 1920s, noticed something in that smear of light. A star. A specific kind of star, one that brightened and dimmed in a slow, regular rhythm like a pulse. Astronomers had discovered a decade earlier that these pulsing stars, Cepheid variable stars, had a remarkable property. The rhythm of their pulsing was directly related to their true brightness. A slow pulse meant a very luminous star. A fast pulse meant a dimmer one. This relationship, once calibrated, worked like a cosmic ruler. If you could see the pulse, you could calculate the true brightness. And if you knew the true brightness, you could calculate the distance simply by comparing how bright it actually was to how faint it appeared from Earth. Hubble measured the Cepheid in Andromeda, and the distance he calculated was staggering. The Andromeda Nebula was not inside our galaxy at all. It was nearly 1 million light-years away, an entirely separate galaxy, vast and self-contained, floating in a space so large the mind genuinely cannot picture it. Our galaxy, the Milky Way, was not the universe. It was one island among many, perhaps among billions. This was 1924. Within a few years, Hubble had measured the distances to more galaxies and noticed something else. Something that would prove in retrospect to be even more significant than the galaxies themselves. The light from almost every galaxy he observed was shifted toward the red end of the spectrum. Researchers had seen this before and understood what it meant physically. It was the Doppler effect applied to light. When a source of light moves away from an observer, the wavelengths of that light stretch, slightly shifting toward longer, redder wavelengths. The same principle that makes a passing siren drop in pitch as it moves away. The galaxies were not merely distant. They were receding, moving away, all of them. And here was the pattern Hubble noticed, the one that changed everything. The further away a galaxy was, the faster it appeared to be moving. Distance and recession speed were not random. They were proportional. For every additional unit of distance, an additional unit of speed. A clean mathematical relationship. What this implied was extraordinary. The universe was not static. It was not a fixed backdrop against which stars and galaxies merely existed. The universe itself, the space between things, was expanding, stretching, growing in all directions simultaneously the way the surface of a balloon grows when you inflate it, carrying every point on its surface further from every other point. Not because the points are moving across the surface, but because the surface itself is getting larger. Evidence suggests this understanding, born from one man's careful measurements of a faint smudge of light, now forms the foundation of modern cosmology. There is something quietly beautiful about the instrument itself. The Hooker telescope at Mount Wilson, through which Hubble made his observations, had a mirror 100 inches across, at the time the largest in the world. It sat at nearly 6,000 feet elevation above the marine layer that often obscured the skies below, and on good nights it could resolve objects of extraordinary faintness. Hubble would work through the night, adjusting the telescope by hand, guiding it carefully to compensate for Earth's rotation, keeping a target star centered in the field for hours at a time. The images were recorded not digitally as we do now, but on glass photographic plates, which he would then study under magnification in the daylight hours. This is the texture of the discovery, not a sudden flash, not a dramatic computation that spat out the answer, but nights of cold patience, plates of glass, and a man looking very carefully at something small and faint, trying to understand what he was seeing. It may be that this is how most genuine understanding arrives, not all at once, but slowly through repeated careful attention, until the meaning of something clarifies like a landscape emerging from fog. What came next in the decades after Hubble was the long, painstaking work of turning an observation into a number. The Hubble constant, as it came to be named, is simply the soap of that relationship. Hubble first noticed the rate at which recession speed increases with distance. Knowing this number precisely would tell scientists how fast the universe is expanding today, and from that how old it is, what shape it has, and ultimately what its fate might be. Getting that number right turned out to be harder than it looked. For much of the 20th century, different teams of astronomers using different methods got significantly different answers. The discrepancies were large enough, a factor of 2 in some cases, that it was genuinely unclear whether the universe was 8 billion years old or 16 billion. This was, among other things, a practical problem. Certain stars had been measured to be older than the universe itself was supposed to be, which was obviously impossible. The field was unsettled, contentious at times, and honest enough to admit it. By the early 2000s, with better telescopes, better calibrations, and decades of refined technique, the large discrepancies had mostly resolved. The Hubble constant had been pinned down to somewhere around 70 kilometers per second per megaparsec, give or take a few units depending on the method used. Researchers breathed something like relief. The major disagreement, it seemed, was closing, and then came Planck. The Planck Space Telescope, operated by the European Space Agency, launched in 2009 with one purpose: to map the cosmic microwave background with unprecedented precision. That ancient afterglow of the Big Bang, the faint warmth that permeates all of space, contains within its subtle variations an extraordinary amount of information about the early universe. The slight temperature differences across the sky, measured to extraordinary accuracy, encode the density and composition of the cosmos when it was only 380,000 years old. From those patterns, physicists can calculate with great confidence what the universe should look like today, including how fast it should be expanding. Planck's answer, published in 2013 and refined in subsequent data releases, was 67 kilometers per second per megaparsec. Meanwhile, the teams using local measurements, Cepheid stars, and a related class of objects called Type 1a supernovae, which also serve as standard candles across cosmic distances, were consistently finding values closer to 73. The gap had returned, and this time both sides had done their work very carefully indeed. What we understand so far suggests that neither measurement is simply wrong. Each has been checked and cross-checked, scrutinized for systematic errors independently replicated by different teams using different instruments and different calibration strategies. The error bars on both measurements, the statistical uncertainty, no longer overlap. They sit apart from each other cleanly and stubbornly at a level of statistical significance that scientists take seriously. The Hubble tension, as it is now formally called, is not a rounding error. It is not a case of one team getting their sums wrong. It is a genuine quantified disagreement between two reliable windows into the same universe, one looking at the universe as it is now, one looking at the universe as it was at the very beginning. And the universe appears to be expanding faster now than its own past predicts it should. This is where the strangeness quietly deepens. If the two measurements were simply measuring slightly different things, or if there was some known source of systematic error affecting one but not the other, the problem would be tractable. Something to fix rather than something to wonder about. But scientists are still exploring every avenue of that kind, and the tension persists, which leaves the more interesting possibility that something in our understanding of the universe itself is incomplete. That there is a layer of physics operating between the early universe and the present day that our current models do not account for. Something that has influenced the expansion, nudged it slightly faster, or altered the conditions in some way in the billions of years since the cosmic microwave background was formed. What that something might be, no one can say with confidence. Some researchers have proposed new particles that existed only in the early universe, briefly altering its dynamics before decaying away. Others have suggested that what we call dark energy, the force thought to be driving the accelerating expansion, may not be as constant as our models assume, that it may vary over time or behave differently at different epochs, that the universe in some subtle way has been changing its own rules as it ages. It seems that every careful look at this problem opens another quiet question. There is a word physicists sometimes use, elegant, to describe a theory that explains much with little. A theory that has a kind of mathematical inevitability to it, a sense that once you see it you understand not just what is true, but why it had to be true. The current standard model of cosmology, called the lambda cold dark matter model, is in many ways exactly that. It takes a small number of parameters, fits them to the best available data, and produces a description of the universe's history and structure that matches observation with remarkable precision. Except for this, except for that stubborn number sitting 6 units above where it should be. The tension does not break the model, it merely unsettles it. Like a painting that is almost perfectly symmetrical but with one small element slightly off-center. You might not notice it immediately, but once you see it you cannot unsee it. And you find yourself wondering whether the asymmetry was accidental, or whether it is pointing to something the painter knew that you have not yet understood. Tonight, somewhere there are astronomers working, checking data, refining calibrations, building the case for a new measurement or a new interpretation of an old one. The James Webb Space Telescope, the largest and most sensitive ever deployed, has already begun its own contributions to this conversation, measuring Cepheids and galaxies with a clarity that was not previously possible. Its early results have so far not resolved the tension. If anything, they've added to the confidence of the local measurements. The universe keeps giving the same answer, and the early universe keeps giving a different one. It may be that the answer, when it eventually comes, will require not a correction to our instruments, but a correction to our ideas. A new piece of physics, a new understanding of what space is, or what time is, or what fills the apparent emptiness between galaxies. Something that once understood will make the current tension feel not like an error, but like a clue that was there all along, patient and quiet, waiting to be recognized. For now, the mystery rests. It rests in the data filed in archives. It rests in the equations circled gently in pencil. It rests in the minds of researchers who lie awake not with worry, but with a particular kind of attention, the kind that comes when you know something important is nearly within reach but not yet. And in a way it rests with you too, because you are part of the universe that is asking this question about itself. Every human mind that has ever looked up and wondered about the stars, about the distance, about what holds everything apart and what draws it together, is the universe, doing what it seems in some quiet way to do naturally, turning its awareness inward, trying to understand its own nature. The light is still travelling, the galaxies are still moving, and the space between everything, including the space between this moment and sleep, is still very gently growing. There is a particular kind of a measurement that requires you to look at two things at once. Not two things in the same room, not two things in the same city or even the same country. Two things separated by such distance that the very concept of simultaneity begins to blur. Two things that exist in the same universe, that are subject to the same physical laws, and yet somehow when you ask them the same question give you different answers. This is where cosmology finds itself tonight, and has found itself quietly for more than a decade. To understand the disagreement fully, not just as a number, but as a thing with texture and weight, it helps to sit with each method of measurement a little longer. To understand not just what each one produces, but how, because the how in this case carries something important. Each method is a kind of language, and the tension between them is not simply a disagreement between numbers. It is a disagreement between two entirely different ways of reading the universe. The first language is local. It speaks in starlight, close enough cosmically speaking to be resolved in detail. The Cepheid variable stars that Hubble used, and that researchers have refined and extended over the past century, are distributed across nearby galaxies. When astronomers measure them, they are reading the universe as it exists in the present era, or close to it. The light from these stars has been travelling for millions of years, not billions. It carries information about the universe as it is now in this relatively recent epoch of cosmic history. The second language is ancient. It speaks in the faint warmth of the cosmic microwave background, that relic radiation left over from a time when the universe was not just young, but unrecognizably different. Hot, dense, filled with a plasma so thick that light could not travel freely through it. For the first 380,000 years of cosmic history, the universe was opaque. Photons of light were constantly absorbed and re-emitted, bouncing through the plasma like sound through a dense material unable to travel any significant distance. And then something changed. The universe cooled. As it expanded, the temperature dropped, and at a critical threshold, roughly 3,000 degrees. Something remarkable happened. The electrons in the plasma, which had been moving too fast to bind with atomic nuclei, slowed enough to be captured. Atoms formed, hydrogen mostly, some helium. The plasma cleared the way a fog lifts on a still morning, and for the first time in the history of the universe, light was free. That light streamed outward in all directions. It has been travelling ever since. In the 13+ billion years since that moment, the universe has expanded so much that the light has cooled and stretched, shifting far down into the microwave part of the spectrum, far beyond what human eyes can detect. But it is still there. It fills the entire sky, uniformly in every direction, a faint afterglow, a memory of the first morning. Researchers have found over decades of increasingly precise measurement that this afterglow is not perfectly uniform. There are tiny variations in temperature of about 1 part in 100,000. that represent the early seeds of all the structure in the universe. The slight overdensities in the primordial plasma that would eventually, over billions of years, collapse under gravity into the galaxies and clusters and filaments we observe today. These fluctuations are not random, they have a pattern, and that pattern is extraordinarily sensitive to the composition of the universe, how much ordinary matter it contains, how much dark matter, how much dark energy, and what the expansion rate was at the time the light was released. By reading that pattern with sufficient precision, physicists can construct a model of the early universe and then project it forward in time, calculating what the expansion rate should be today. That is what the Planck satellite did with exquisite care over 4 years of observation. What we understand so far suggests the two measurements are not simply imprecise. They are precise impressively so. The uncertainty on the local measurement based on Cepheids and supernovae is now around 1%. The uncertainty on the cosmic microwave background measurement is comparable, and they disagree by approximately 8 to 9%. The gap is roughly 5 times larger than the combined uncertainty. In the language of statistics, this is expressed as a significance level. Physicists speak of this tension as sitting at roughly 5 sigma, meaning there is roughly a 1 in a million chance the disagreement is due to random variation. A result at 5 sigma in particle physics is the traditional threshold for claiming a discovery. Here it is the threshold of a mystery. It may be that such numbers feel abstract in the quiet of the night, and that is fine. What they mean stripped of the technical language is simply this. The universe measured 2 different ways gives 2 answers that should not both be right, and both are. There have been many attempts, careful and creative, to find the error, to locate the flaw in one chain of reasoning or the other that would bring the 2 into agreement. The Cepheid method, for instance, depends on a calibration chain, a sequence of distance measurements, each building on the last, that extends from nearby stars all the way to distant galaxies. Each step in that chain is an opportunity for a small error to accumulate. Researchers have examined every link with great thoroughness, the distances to the calibrating stars, the relationship between pulsation period and luminosity, the corrections for dust and metallicity that can affect the apparent brightness of stars. The James Webb Space Telescope has now contributed its own measurements to this effort, resolving Cepheids in galaxies previously too distant to study with clarity. The results so far have held. The local measurement remains near 73. On the other side, the cosmic microwave background analysis depends on assumptions about the content of the early universe. The proportions of ordinary matter, dark matter and dark energy, the nature of the initial fluctuations, the physics of the plasma before recombination. These assumptions are embedded in a model, and a model is always in some sense an approximation. Scientists are still exploring whether small modifications to the standard model, additional species of neutrinos for example, or an early period of slightly different dark energy might bring the prediction in line with observation. So far, no modification found has resolved the tension without creating new problems elsewhere. There is a concept in physics called a crisis. It sounds alarming, but physicists use the word almost affectionately. A crisis is not a failure. It is a sign of health evidence that the field has reached the edge of what its current understanding can explain and that something new is needed. The history of physics is in large part a history of productive crises. In the late 19th century, classical mechanics and the newly developing theory of electromagnetism gave contradictory predictions about the speed of light. That crisis produced special relativity. Around the same time, the failure of classical physics to explain how heated objects radiate energy, the so-called ultraviolet catastrophe, led directly to quantum mechanics. 2 of the most transformative theories in the history of science emerged directly from measurements that wouldn't agree. It seems that disagreements of this kind, when they refuse to resolve, have a tendency to point somewhere genuinely new. The Hubble tension may be another such pointer. Not a failure of the instruments, not a failure of the mathematics, but a finger extended toward physics that doesn't yet exist in any textbook. Toward a layer of reality that human beings have not yet learned to describe. There is something in the act of measuring that is itself worth holding for a moment. To measure the expansion rate of the universe, you must first decide what counts as a reliable standard. A ruler works only if you trust that a meter today is a meter everywhere and always. In the everyday world, this assumption is unproblematic. But cosmology is not the everyday world. It spans 13 billion years of time and billions of light years of space. The assumption that physical constants have remained constant, that the properties of atoms and light and gravity are the same today as they were in the early universe, is not obviously true. It is an assumption that has been tested and in most respects confirmed. But it is still ultimately an assumption. Some researchers have wondered whether the tension might be pointing to a subtle change in fundamental constants over cosmic time. Whether the universe of the early era was in some precise and measurable way physically different from the universe of today. Not dramatically different. Nothing about the stars or the galaxies or the basic mechanics of gravity would need to change. Just slightly different in ways that would be nearly impossible to detect except through exactly the kind of tension we are discussing. It is as yet a possibility rather than a solution. Evidence suggests the universe is consistent with constant physics across most of its observable history, but the most precise edges of that consistency are still being mapped. What remains when you step back from the technical details is something with a particular texture. Not alarm, not confusion. Something more like the feeling of standing at the edge of a known map, where the cartographers have written "not here be dragons," as the old maps sometimes did, but simply left the space unfinished. Blank not from ignorance of its existence, but from an honest acknowledgement that it has not yet been explored. The universe has that quality tonight, known in so many ways, measured with extraordinary precision, described by equations that have been tested 1,000 times over, and yet at the edges still open, still offering the peculiar gift of genuine uncertainty, the kind that does not create anxiety but something more like wonder, the kind that makes you feel quietly that there is still more to find. Every measurement is also a kind of attention, a way of saying this matters, this is worth looking at carefully. Spend your time and your resources and your patience on this, and the universe, it seems, responds to that attention by gradually, carefully revealing itself. Not all at once, never all at once, but slowly, the way trust is built through repeated, careful showing up. Tonight the telescopes are still pointed upward. The data is still being collected, refined, debated. Somewhere a graduate student is running a new analysis on an old data set. Somewhere a theorist is sketching an equation that may in a few years become the seed of a new understanding. The work continues unhurried and patient the way the universe itself moves, and the number sits there quietly insisting on itself. 7367. Two rulers laid end to end across the history of time, differing by just enough to mean everything. There is a gentleness in not knowing, a kind of spaciousness. When the answer has not yet arrived, the question is still alive, still open to possibility, still capable of becoming something surprising. The Hubble tension in this way is not an ending. It is the universe still in conversation with itself. And the quieter question, the one that stays long after the measurements have been put away, is not which ruler is wrong. It is what kind of universe would need both of them to be right. And what scientists discovered next as they looked not outward at the stars but deeper into the fabric of the cosmos itself is something stranger and more intimate than distance. A darkness that does not merely surround the universe but fills it quietly and visibly from the inside out. Some things only become visible when you stop looking for them directly. The expansion of the universe was like that. Hubble saw it in the light of galaxies. The cosmic microwave background encoded it in patterns of temperature across the entire sky. 2 measurements, 2 eras, 2 different windows, and yet the same universe behind both of them. Except the numbers don't quite match. And that small mismatch has led physicists somewhere unexpected. It has led them to ask not just how fast the universe is expanding, but what is making it expand at all. For most of human history, gravity was the story of the universe. The force that pulls things together, that holds planets in their orbits, collapses clouds of gas into stars and draws galaxies into clusters. Gravity was the dominant narrative. And when Einstein completed his general theory of relativity in 1915, he gave that narrative its most complete mathematical form. Space and time were not a fixed backdrop, he showed, but a flexible fabric curved by mass and energy shaping the paths of everything moving through it. Einstein's equations were extraordinarily powerful. They described in elegant geometry how matter tells space how to curve and how curved space tells matter how to move. The orbits of planets, the bending of light around massive objects, the behavior of black holes, all of it followed naturally from the mathematics. But when Einstein applied his equations to the universe as a whole, he encountered a problem. The equations kept producing a universe that was either expanding or contracting. They refused to allow a static universe, the kind that most people, including Einstein himself, assume the cosmos to be. So he made an adjustment. He added a term to his equations, a mathematical constant, a kind of cosmic pressure that counterbalanced gravity and held the universe still. He called it the cosmological constant, and for over a decade it sat quietly in the equations doing its job. Then Hubble showed that the universe was expanding after all. And Einstein, in what he reportedly called the greatest mistake of his life, removed the constant from his equations. It came back. Not immediately, but in 1998, 2 independent teams of astronomers studying those Type 1a supernovae made the discovery that would reshape cosmology. They were trying to measure the rate at which the expansion of the universe was slowing down. Everyone assumed it must be slowing. Gravity pulls things together and the matter in the universe should be acting as a brake on its own expansion. The question was simply how strong the brake was. What they found instead was that the expansion was not slowing, it was speeding up. The distant supernovae were fainter than they should have been, dimmer than the expansion rate predicted. They were further away than expected, which meant the universe had been expanding faster in the recent past than in the more distant past. Something was pushing space apart and it was getting stronger over time, or at least not weakening. Researchers named this force dark energy. Not because it is dark in the visual sense, but because it is unknown, invisible, undetectable by any direct means currently available. Its existence is inferred entirely from its effect on the expansion, the same way you might infer the presence of wind, not by seeing it, but by watching how it moves everything around it. What we understand so far suggests that dark energy constitutes approximately 68% of the total energy content of the universe. Nearly 7/10 of everything that exists in energetic terms is this thing we cannot see, touch, or measure directly. Ordinary matter, the atoms that make up stars, planets, galaxies, and every living thing, accounts for less than 5%. The remaining 27% is another mystery dark matter, which we will return to gently in its own time. For now, dark energy. The simplest mathematical description of dark energy is that it behaves exactly like Einstein's cosmological constant, a fixed uniform energy density that permeates all of space. Equally, does not dilute as the universe expands and exerts a kind of negative pressure that drives expansion rather than opposing it. When physicists plug this value into their models of the universe and fit it to all available observation, it works remarkably well. It explains the accelerating expansion. It produces a universe whose age, geometry, and large-scale structure match what we observe. It seems that Einstein's greatest mistake may have been removing his correction in the first place. But here is where the quiet difficulty lives. When physicists try to calculate what the cosmological constant should be using the tools of quantum mechanics, which describes the behavior of energy at the smallest scales, they arrive at a number. And that number is wrong, not slightly wrong, not off by a factor of 2 or 10. The theoretical prediction from quantum mechanics differs from the observed value of dark energy by a factor of approximately 10 raised to the power of 120. This is by any measure the largest discrepancy between theory and observation in the history of physics. It has its own name, the cosmological constant problem, and it has remained unresolved for decades, sitting at the intersection of general relativity and quantum mechanics like a splinter that no one has been able to remove. It may be that the theoretical calculation is missing something fundamental. That quantum mechanics in its current form overcounts the energy of empty space in a way that does not translate directly into gravitational effects. Or it may be that dark energy is not a cosmological constant at all, not a fixed property of space, but something more dynamic, something that evolves. This is where a concept called quintessence enters the picture quietly without drama, which seems appropriate for something named after the fifth element of ancient philosophy. Quintessence is a theoretical framework in which dark energy is not a fixed constant but a field, a dynamic quantity spread through all of space, capable of varying in strength over time and possibly across different regions of the universe. Unlike the cosmological constant, which is the same everywhere and always a quintessence field, would have its own equations of motion. It could be stronger in some epochs, weaker in others. It could leave subtle signatures in the structure of the universe that with precise enough measurements might be detectable. Evidence suggests that current observational data cannot yet definitively distinguish between a cosmological constant and a slow-moving quintessence field. The difference, if it exists, is subtle enough to hide within the uncertainties of current measurements. But upcoming surveys, vast mapping projects that will catalogue hundreds of millions of galaxies and measure the cosmic expansion with unprecedented precision are specifically designed to look for exactly this kind of variation. Scientists are still exploring whether dark energy is fixed or fluid, whether the cosmological constant is truly constant, whether the universe has one energy density driving its expansion or something more restless and alive. And here is the thread that connects all of this back to where we began. If dark energy is not constant, if it has been changing even slowly over the history of the universe, then the early universe and the late universe would have been expanding under slightly different conditions. The cosmic microwave background, which encodes the state of the universe at 380,000 years old, would be measuring a universe under one set of conditions. The Cepheids and supernovae, which measure the universe as it is today, would be measuring a universe under another set of conditions. And the two measurements would give different answers for what appears to be the same quantity, which is of course exactly what we observe. This does not mean the explanation is correct, it is one possibility among several. But researchers have found that even small variations in the behavior of dark energy over cosmic time variations well within the range of current theoretical models could in principle account for the Hubble tension, a universe that is not quite the same universe it was, expanding to a slightly different rhythm than its own past would predict, carrying within its present state some faint record of a change that happened so gradually over so many billions of years that no single instrument could catch it in the act. There is something almost recognizable in that. The way things change so slowly that the change itself becomes invisible. The way a river gradually carves a canyon not through any single dramatic event, but through the patient accumulation of small moments, each one almost imperceptible together, amounting to something that reshapes the landscape entirely. It may be that the universe works this way too, not through sudden transformation, but through the slow, continuous pressure of forces that are always present, always operating, always quietly reshaping the fabric of everything. And the fact that we are only now beginning to detect the edges of that slow change, only now developing instruments sensitive enough to notice a discrepancy of 6 units across 13 billion years of history, says something about where we are in the story of human understanding. Not at the end, not even close. The James Webb Space Telescope has been looking at Cepheids in distant galaxies with a clarity that was previously impossible. Its mirrors are cold and still in the darkness between Earth and the Sun, capturing light that has travelled for billions of years, resolving individual stars in galaxies so remote they appear as faint smudges to smaller instruments. Its early findings have not resolved the tension. The 73 holds. The measurement is precise and the calibration is careful, and the answer is not 67. Somewhere in that gap in those 6 quiet units is a physics we don't yet know. A piece of the universe that has been operating all along, shaping everything, leaving its trace in the data, waiting for the right question to be asked in exactly the right way. The universe is patient. It has been carrying this secret for 13 billion years. It can wait a little longer, and as the mind begins to loosen its grip on the details, as the numbers soften into impressions, and the distances blur into something more like feeling, it becomes possible to sense that the question itself is a kind of companion, present and unhurried, drifting alongside you in the dark. Something about the way empty space holds energy quietly without announcement has always been true. The universe knew it long before anyone thought to ask. There is a kind of solace that isn't empty. The silence between galaxies, the silence inside an atom, the silence of space that isn't really space at all, but something far stranger, a field, a fabric, a medium that hums with the kind of latent energy that nothing in everyday experience prepares you to imagine. We've been drifting gently through the large questions, the expansion, the tension, the dark energy that fills the universe without being visible in any conventional sense. But there is another darkness out there, a different kind of missing thing. And unlike dark energy, which pushes everything apart, this one holds everything together. It was noticed first not in the sky, but in the math. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying a collection of galaxies known as the Coma Cluster, a dense gathering of hundreds of galaxies bound together by gravity approximately 320 million light-years from Earth. Zwicky was trying to measure how fast the individual galaxies within the cluster were moving relative to one another. He used the Doppler shift of their light, the same principle that had revealed the expansion of the universe, to calculate their velocities. What he found didn't add up. The galaxies were moving far too fast. In a gravitationally bound system, the speed at which objects orbit the center depends on the total mass of the system. The faster something is moving, the more gravitational force is needed to keep it from flying off into space. Zwicky calculated the mass of the Coma Cluster from its visible light, counting the galaxies, estimating their stellar content, and compared that to what the galaxy velocities implied the mass must be. The visible mass was roughly 400 times too small. Zwicky suggested that there must be additional mass in the cluster mass that was not emitting light, that was invisible to his telescope, but that was gravitationally present. He called it Dunkel Materia, dark matter. The idea was noted, filed away, and largely ignored for several decades. It came back with force in the 1970s through the work of an astronomer named Vera Rubin. Rubin was studying the rotation of spiral galaxies, measuring how far stars at different distances from the galactic center were orbiting. This is a well-defined physics problem. In our own solar system, the planets closest to the Sun orbit fastest, and the speed drops off predictably, with distance a pattern described precisely by Newton's laws and Einstein's refinements. The same should hold for galaxies. Stars near the bright massive center should orbit quickly. Stars far out in the sparse outer disk should orbit slowly. Rubin measured galaxy after galaxy and found something that refused to behave as expected. The rotation curve's graphs of orbital speed versus distance from the center were flat. Stars in the outer regions of galaxies were orbiting just as fast as stars near the center, not slowing down, not following the pattern that the visible mass alone would produce. For this to be possible, there had to be additional mass, not concentrated at the center where the visible stars and gas were clustered, but spread through an enormous invisible halo extending far beyond the visible disk of the galaxy. A sphere of unseen material enveloping the entire structure, providing the gravitational scaffolding that kept the outer stars from flying away into intergalactic space. Evidence suggests this invisible halo is real, and it is not small. For a typical spiral galaxy, the dark matter halo is estimated to be far larger than the visible disk, perhaps 10 to 15 times as massive as all the stars and gas combined. Researchers have found this signature in galaxy after galaxy, in cluster after cluster in the large-scale structure of the universe itself. Dark matter does not emit light. It does not absorb light. It does not interact with ordinary matter. Through electromagnetism, the force that governs how most particles interact with their environment, it passes through everything. Through planets, through people, through the entire Earth, without any detectable effect, leaving only the faint trace of its gravity behind. Right now, in this moment, dark matter is passing through you, through the walls of whatever room you are in, through the floor and the ground beneath it. In unimaginable quantities, scientists suggest that approximately 1 billion dark matter particles pass through a space the size of your thumbnail every single second if current theoretical models are correct. You feel none of it. It leaves no impression on the nerves, no warmth, no pressure. It is the most intimate stranger imaginable. What is it made of? This is the question that has occupied particle physicists and cosmologists for 50 years, and the answer remains genuinely unknown. The leading theoretical candidate for much of that time has been a class of hypothetical particles called weakly. Interacting massive particles with significant mass but almost no interaction with ordinary matter beyond gravity. These particles arise naturally from certain extensions of the standard model of particle physics. The framework that describes all known fundamental particles and forces and their predicted properties would make them exactly the kind of dark matter that cosmological observations require. Enormous detectors have been built to find them. Underground laboratories shielded from cosmic rays by miles of rock filled with ultra-pure materials monitored by exquisitely sensitive instruments waiting for the rare occasion when a dark matter particle might scatter off an atomic nucleus and leave a detectable signal. It seems that these experiments have been running for decades now, growing more sensitive with each generation, and no confirmed signal has arrived. This has not disproven the existence of dark matter. It has only constrained the properties that dark matter can have. Each null result rules out a portion of the theoretical parameter space, narrowing the possibilities, focusing the search. Other candidates have been proposed. Axion's extraordinarily light particles, originally hypothesized to solve an entirely different problem in particle physics, but which would also behave as dark matter. Sterile neutrinos, hypothetical heavier cousins of the known neutrino family, which interact even more weakly than their relatives. Primordial black holes. Black holes formed in the dense early universe before stars existed, which would be dark, massive, and essentially invisible to most observation techniques. Each of these possibilities has its own experimental searches, its own predictions, its own way of hiding just beyond the edge of current instrumentation. The mind quietly registers in considering all of this that the universe has arranged things in a way that makes its own composition remarkably difficult to read. It may be that this is simply how physics works at these scales, that the universe does not volunteer its secrets, it withholds them until the question is asked with sufficient precision, with the right instrument at the right moment. What researchers have found in studying dark matter through its gravitational effects is that it's not randomly distributed. It forms structures, it clusters collapses under its own gravity, and creates the scaffolding along which ordinary matter is gathered. The large-scale structure of the universe, the vast cosmic web of filaments and voids and nodes that maps the distribution of galaxies across billions of light-years, traces the underlying distribution of dark matter almost perfectly. In computer simulations, when physicists model the universe's evolution beginning from the conditions encoded in the cosmic microwave background, including both ordinary matter and dark matter, but excluding dark matter causes everything to fall apart. The galaxies don't form. The filaments don't appear. The structure we observe doesn't emerge. Add dark matter back in the right proportions and the simulated universe grows to look strikingly like the real one. This is perhaps the most compelling evidence for dark matter's existence. Not any single observation, but the overall coherence of a model that requires it. Without dark matter, the universe as we see it, the galaxies, the clusters, the vast interconnected web is simply not reproducible. There is something that settles gently when you consider this. The visible universe, everything we can see, everything that glows and burns and emits light across all wavelengths is in some sense a thin luminous film on the surface of something much larger and much darker. The true skeleton of the cosmos is invisible. The majority of the mass that shaped every galaxy, that guided the formation of every star and planet and eventually every living thing, is matter we have never seen and cannot directly touch. We are embedded in something we cannot perceive, surrounded by it, supported by it in the most literal structural sense, because without dark matter's gravitational architecture, the galaxy we inhabit would never have formed. The solar system would never have coalesced. The conditions for life would never have assembled themselves. Dark matter made us possible, and we have no idea what it is. Psychologists often note that human beings are remarkably good at orienting themselves to what they can see and touch, at building mental maps from visible, tangible landmarks. What dark matter asks of us is something different. It asks us to hold space for the real without being able to perceive it directly, to trust the mathematics, to follow the curve of a rotation graph to its logical conclusion even when that conclusion leads somewhere invisible. Scientists are still exploring whether dark matter is a single type of particle or a whole sector of unknown physics, a hidden world of particles and forces that mirrors the ordinary world, but interacts with it only through gravity. Some models suggest this possibility, a dark sector as it is sometimes called, with its own internal complexity, its own chemistry, its own dynamics running parallel to everything we know, interpenetrating everything we are utterly silent. The universe may be more populated than it appears, and here in the stillness of that thought, something becomes clear about the nature of the problem we have been tracing together. The Hubble tension, dark energy, dark matter. These are not three separate puzzles sitting neatly in separate boxes. They are three windows into the same deep uncertainty, three places where the known universe gestures beyond itself, where the mathematics requires something more, where the data arrives at the edge of current understanding and keeps going. What we understand so far suggests that roughly 95% of the universe is made of things we have not yet characterized. 5% is the stars, the gas, the planets, the dust, the atoms. Everything visible, everything measured, everything we have named and studied for centuries. The other 95% is elsewhere, structurally present, gravitationally indispensable, and essentially unknown. This is not a failure. It is an inheritance. A map with most of the territory still blank handed from one generation of scientists to the next, each generation filling in a little more, each generation discovering that the blank space is larger and stranger than the one before them imagined. The night holds this knowledge comfortably. There is no urgency in the dark matter question tonight, no deadline. The particles are passing through regardless, patient, indifferent, carrying on with whatever they carry on with in their invisible parallel existence. The universe does not require your understanding in order to continue. You can rest alongside the unknown. Let it drift past the way the dark itself drifts through an open window, not intrusive, not demanding, simply present. Part of the same fabric as the warmth and the quiet and the slow release of a day. And in the patterns of how matter gathers, how invisible things leave visible traces, how structure emerges from what cannot be seen, there may be something familiar waiting closer than the stars.
There is a moment sometime just before sleep arrives when the mind does something strange. It loosens. The thoughts that felt urgent an hour ago begin to lose their edges. The to-do lists and the replayed conversations and the small anxieties of the day, they don't disappear exactly, but they stop insisting. They float a little. And in that floating, something else becomes briefly perceptible, a kind of background hum. A sense that the mind is larger than its contents.
Scientists have a name for what happens in that transitional state. But before we arrive there, we need to go somewhere else first. Somewhere much older and much colder than anything on Earth. We need to go back to the beginning of light itself. Imagine a universe with... Not a universe waiting for stars to form a universe that has no mechanism yet to form them. No condensed matter. No gravitational seas around which gas might slowly accumulate and collapse. Just a hot, dense, rapidly expanding plasma cooling, as it stretches thinning as it grows. This is the universe as it was in its first few 100,000 years, before a single photon had ever travelled more than a short distance without being scattered, before anything like structure existed anywhere, and then, as we have touched on before, the clearing. The moment when neutral atoms formed and light was finally free. What happened in the moments after that clearing is in some ways as remarkable as the clearing itself, because the universe that emerged from the plasma was not smooth. It was not perfectly uniform. The quantum fluctuations of the earliest moments, fluctuations so small, they existed at the scale of particles at the very edge of the Heisenberg uncertainty principle, had been stretched by the rapid expansion of the early universe into variations in density that spanned enormous distances. Some regions were very slightly denser than average, others were very slightly less dense. These tiny differences, temperature variations of 1 part in 100,000 in the cosmic microwave background, were the seeds of everything. Gravity is patient, and over hundreds of millions of years it worked on those seeds. The slightly denser regions attracted more matter. More matter increased the local gravity. Increased gravity attracted more matter still. The process was slow at first, almost imperceptibly slow, operating across distances so vast that nothing seemed to be happening. But time compounded the effect. Slowly filaments of matter began to form along the densest threads of the dark matter scaffolding. Gas accumulated. It cooled, it collapsed, and then somewhere between 300 million and 500 million years after the Big Bang, in a region of collapsed gas that had grown dense enough and hot enough at its core, something ignited. The first star. Researchers have not directly observed the first stars. They existed too long ago, and the light from that era has been stretched by the expansion of the universe into wavelengths that current instruments have struggled to capture with clarity. But evidence suggests from theoretical models and indirect observations that these first stars were very different from the stars we know today. They were enormous, perhaps hundreds of times more massive than our Sun, and they burned with an intensity that could not last. They lived for only a few million years, which in cosmic terms is barely an exhale, and then they died in explosions of almost incomprehensible violence. Those deaths mattered more than the lives. When massive stars exhaust their fuel, they collapse catastrophically and then rebound, sometimes in explosions called supernovae, sometimes in even more energetic events. In the cores of these dying stars, under conditions of unimaginable pressure and temperature, nuclear fusion had been building heavier and heavier elements. Hydrogen fused into helium, helium into carbon, carbon into oxygen, neon, silicon, and eventually iron, the element at which fusion stops producing energy and begins consuming it, causing the core to collapse. The explosion that followed scattered everything the star had built, all those newly forged elements, into the surrounding space. Carbon, oxygen, nitrogen, silicon, iron, the raw materials of planets, of chemistry, of biology. Every carbon atom in your body was forged in the core of a star that no longer exists. Every oxygen atom you are breathing tonight was released into space by a stellar explosion that predates the solar system by billions of years. The calcium in your bones, the iron in your blood, the phosphorus in every strand of your genetic material, all of it was processed inside stars scattered by their deaths, gathered by gravity, incorporated into the nebula that eventually became the Sun and its planets, and eventually through billions of years of chemistry and biology into you. It seems that we are not made of the universe the way a painting is made of canvas. We are made of the universe the way a wave is made of the ocean, continuously, inseparably from the inside. The process by which elements are forged inside stars is called stellar nucleosynthesis, and its details are among the most precisely understood things in all of astrophysics. The abundances of different elements in the universe, how much helium exists relative to hydrogen, how much carbon relative to oxygen match the predictions of nucleosynthesis theory with extraordinary accuracy. This is one of the great confirmations in science, a theoretical framework constructed from nuclear physics applied to conditions inside stellar cores produces element ratios that match what we observe in the universe to remarkable precision. What researchers have found in the decades since this framework was established is that the process did not end with the first generation of stars. Each generation of stars was born from gas, enriched by the deaths of its predecessors. Each generation built heavier elements and scattered them more widely. The universe has been slowly enriching itself, metallizing itself. Astronomers sometimes say, using a term that includes all elements heavier than helium across the full arc of cosmic time, our Sun is a third-generation star, or possibly later. The gas cloud from which it formed had already been through multiple cycles of stellar birth and death, and it carried within it the accumulated output of all those previous generations. This is why Earth exists with the chemical complexity it has, why the table of elements includes not just hydrogen and helium, which is mostly what a first-generation universe contained, but the full range of atoms that chemistry and biology require. The universe had to age before life was possible. This is not a minor observation. It means that the conditions for life, for chemistry, for planets, for the slow emergence of self-replicating molecules could not have existed in the early universe. The necessary ingredients had not yet been made. The universe had to go through at least one full generation of stars, and probably several, before the raw materials for biology were sufficiently distributed through the cosmos. We exist at a particular moment in cosmic history, not the beginning, not the end, but a middle epoch when the universe is old enough to have produced the chemistry of life and young enough that stars are still burning, that the night sky is still populated with light, that the energy available to living systems has not yet been exhausted. It may be that this window, this particular era in cosmic history, when life is possible, is not infinitely long. Stars will eventually exhaust the available hydrogen. The last stars will cool and go dark, the universe will continue expanding, growing emptier and colder, trending toward a long, still equilibrium that cosmologists sometimes call the heat death. Not a violent end, but a slow fading. The universe not going out with a bang, but simply becoming too thin and cool for complexity to persist. That is by current estimates an almost incomprehensibly distant future. Tens of trillions of years away at minimum. The universe has barely begun by that accounting, but here tonight stars are burning. Right now, while you rest, the Milky Way contains somewhere between 100 billion and 400 billion stars. The uncertainty in that estimate is itself a measure of how vast and difficult to survey our own galaxy is. Each of those stars is a nuclear furnace converting hydrogen into helium at its core, releasing energy that eventually becomes light, maintaining the temperature and pressure of its outer layers against the inward pull of its own gravity. The Sun, our nearest star, our primary source of energy. The centre of the solar system converts approximately 600 million tons of hydrogen into helium every single second. A fraction of the energy released in that process eventually reaches Earth as sunlight. A fraction of that is captured by plants. A fraction of that is incorporated into the food chains that support every living thing on this planet. The chain is long and the losses at each step are enormous, but the chain holds. It has held for 4.5 billion years and it shows no sign of breaking anytime soon. There is a deep steadiness in that. Not the steadiness of something frozen in place, but the steadiness of something burning reliably, a process so continuous and so consistent that its continuity itself becomes a kind of background fact, a constant that you stop noticing precisely because it never stops. The structure of the universe, the dark matter scaffolding the filaments of ordinary matter, the galaxies gathered at their intersections, the stars scattered through those galaxies in numbers that exceed ordinary human imagination. All of it emerged from those tiny quantum fluctuations in the first fraction of a second of existence. The brain tends to simplify this into something more manageable, a story with a beginning, a development, a present moment. But the reality is less linear and more layered. The quantum fluctuations and the large-scale structure and the nuclear burning in stellar cores and the carbon in your body are not sequential events so much as nested processes, each one a different time scale of the same unfolding. The universe has been elaborating on its opening conditions for nearly 14 billion years. Every structure, every element, every chemistry, every biology is a consequence of those first moments, amplified, transformed, compounded across time into something that can, in certain fortunate configurations, look back at its own origin and wonder about it. What we understand so far suggests that this capacity for self-reflection for a universe to produce structures that ask questions about the universe is not incidental. It is one of the things the universe does given enough time and the right conditions. It emerges from chemistry and biology through processes whose details we understand increasingly well, but whose overall significance remains genuinely open. The cosmic microwave background encodes the conditions that made all of this possible. The Hubble tension hints that something in those conditions or in their development is not fully understood. The dark matter that structured the galaxies is passing through you right now. The carbon in your cells was forged in a stellar core. The oxygen in your lungs was scattered by a stellar death. You are in the most literal and material sense a product of everything we have been slowly tracing together tonight. And that without any drama is a remarkable thing to carry into sleep. There is a quieter layer to all of this one that doesn't live out in the distant galaxies or the dying stars, but in the first light that ever crossed the universe freely. And what that ancient light has encoded in patterns so subtle they took decades to read is something that reaches all the way back to before the stars were born. Light has a memory, not in the way that living things have memory, not stored, not retrievable, not waiting to be recalled on a quiet evening, but in the sense that light carries within itself the complete record of everything it has passed through and everything it has touched. Every interaction leaves a trace. Every absorption and re-emission, every scattering event, every journey through a region of space with particular properties, all of it is encoded in the light that eventually arrives at the other end. The cosmic microwave background is the oldest light we can access, and what it has remembered, what it carries encoded in the subtle temperature variations across the entire sky, is a portrait of the universe at a moment so early that nothing we would recognize as structure yet existed. No stars, no galaxies, no planets, only a vast cooling plasma just beginning to release its first free photons into a universe that had never before been transparent. Reading that portrait has taken decades, and what it says is still being translated. The Planck satellite, which produced the most precise map of the cosmic microwave background yet made, was not a large instrument by the standards of ground-based telescope. It was roughly the size of a large wardrobe, and it travelled to a point in space called the second Lagrange point, a location approximately 1.5 million kilometres from Earth on the opposite side from the Sun, where the gravitational influences of the Earth and Sun balance in a way that allows a spacecraft to maintain a stable position relative to Earth while orbiting the Sun. From that vantage point, shielded from the warmth of the Sun and Earth, cooled to temperatures colder than almost anywhere else in the solar system, Planck spent 4 years scanning the entire sky with detectors sensitive enough to measure temperature differences of a millionth of a degree. What it produced was a map, a full sky portrait of the cosmic microwave background rendered in false color to make the tiny temperature variations visible to human eyes. Hotter regions appear in one color, cooler regions in another, and the pattern of those variations, the particular statistical distribution of their sizes and shapes and amplitudes, encodes an extraordinary amount of information about the universe at the moment the light was released. Researchers have found in analysing this pattern that it matches theoretical predictions with a precision that is almost unsettling in its accuracy. The physics of what produced those patterns is intricate, but its outline is approachable. In the dense plasma of the early universe, before the clearing ordinary matter and light were tightly coupled, they interacted so frequently that they behaved essentially as a single fluid. This fluid was subject to two competing forces. Gravity pulled it inward, trying to compress the denser regions further. Radiation pressure, the pressure exerted by the intense light trapped within the plasma, pushed outward, resisting compression. The result was oscillations. Acoustic oscillations, physicists call them sound waves in a sense, though the medium was plasma rather than air, and the wavelengths were measured in millions of light years rather than centimeters. Dense regions would compress, reach a maximum, then rebound and expand, reach a minimum, then compress again. The frequency of these oscillations depended on the composition of the plasma, the ratio of ordinary matter to radiation, the presence of dark matter, the overall geometry of the universe. When the clearing occurred, these oscillations were frozen in place, and the light that escaped at that moment carried within it the snapshot of where every oscillation was in its cycle. And those frozen oscillations appear in the cosmic microwave background as a characteristic pattern of hot and cold spots at particular angular scales. The pattern is called the power spectrum, and it is in essence a fingerprint of the early universe's composition. What the power spectrum tells us is precise and remarkable. The universe at recombination, the moment of the clearing, contained ordinary baryonic matter at a density of approximately 5% of the total energy content. Dark matter at approximately 27%, radiation at a very small fraction, and the remainder the dominant component even at that early stage in a form consistent with what we now call dark energy, or the cosmological constant. These proportions extracted from the acoustic oscillation pattern in the cosmic microwave background are consistent with everything else we observe about the universe. The large-scale structure, the abundances of light elements, the age of the oldest stars. The concordance is remarkable. A single set of 6 parameters fit to the pattern in the ancient light correctly predicts an enormous range of independent observations across 13 billion years of cosmic history. This is the lambda cold dark matter model, and it is both the most successful cosmological model ever constructed, and the model that contains unresolved at its core the Hubble tension we have been tracing throughout this night. The tension lives in a specific place within the model. When physicists use the Planck power spectrum to predict the Hubble constant to calculate what the expansion rate should be today, given the conditions at recombination, they arrive at 67. When astronomers measure the expansion rate directly using Cepheid stars and supernovae calibrated against local distance measurements, they arrive at 73. The model that agrees with everything else disagrees here, and the disagreement has survived every attempt to resolve it through instrumental correction or recalibration. What we understand so far suggests there are 3 broad categories of explanation, and none of them is yet confirmed. The first is that there is an unidentified systematic error somewhere, a subtle bias in either the cosmic microwave background analysis or the local distance measurements that has not yet been detected and corrected. This would be the least consequential explanation. It would mean the universe is behaving as expected, and the problem is with our instruments or our data reduction. Scientists are still exploring this possibility, but with diminishing optimism. The measurements have been refined too many times by too many independent groups to make a simple systematic error the comfortable answer. The second category is early universe physics. Something that happened before or during recombination, a new particle, a new interaction, a brief episode of altered physics that changed the conditions in a way the standard model does not include. If the sound horizon, the maximum distance those acoustic waves could have travelled before the clearing was different from what the standard model predicts, then the calibration of the cosmic microwave background measurement would shift, and the resulting Hubble constant would be different. Several theoretical proposals fall into this category. Early dark energy is one, a hypothetical component that existed only in the early universe, briefly increasing the expansion rate before recombining or decaying away. Interacting dark matter is another, a model in which dark matter was not entirely inert in the early universe, but had subtle interactions that modified the acoustic oscillations. The third category is the most open-ended. It suggests that the tension is pointing to something genuinely new, a modification of the laws of physics at cosmological scales, or a new understanding of gravity itself, or a feature of the universe's structure that our current framework simply does not have room for. General relativity has been tested with extraordinary precision on scales ranging from laboratory experiments to the orbits of binary pulsars to the detection of gravitational waves from merging black holes. On all these scales it holds, but cosmological scales, the behavior of gravity across billions of light years operating over billions of years of time, are genuinely different from anything that has been directly tested. It may be that gravity behaves slightly differently on those scales than Einstein's equations predict. Modified gravity theories have been proposed frameworks in which the equations of general relativity are adjusted in ways that become significant only at very large distances or very low accelerations. Some of these modifications could in principle produce an apparent tension between early and late universe measurements without requiring any new particles or exotic energy components. The mind quietly registers, in holding all of these possibilities at once, that the universe is not obligated to fit neatly into any of them. It will be what it is. The correct explanation may be one of these, or a combination, or something not yet imagined. There is a particular quality to unsolved problems in fundamental physics. They are not like unsolved engineering problems where the path forward is clear, even if the work is difficult. Fundamental physics problems are more disorienting than that. They sit at the edge of the conceptual framework itself, in the places where the framework runs out of things to say, where the equations return undefined results or contradictory predictions, where the physical intuition built up over decades of successful theorizing quietly stops functioning. The Hubble tension is that kind of problem. It does not tell you what is wrong, it only tells you that something is. It points outward into a region of physics where the usual landmarks are absent, where the path forward requires building new conceptual tools before you can even clearly state what you're looking for. Evidence suggests this is how the deepest advances in physics have always begun, not with a clear question and an uncertain answer, but with a strange result that resists interpretation, that refuses to fit, that keeps returning no matter how the instruments are improved, that eventually forces a reorganization of the underlying ideas. The ultraviolet catastrophe that led to quantum mechanics, the constant speed of light that led to special relativity, the perihelion precession of Mercury that general relativity eventually explained. Each of these was for a time simply a number that didn't fit. A small discrepancy, a 6-unit gap between expectation and measurement. The cosmic microwave background has given us so much. It has confirmed the age and geometry of the universe. It has revealed the composition of the early cosmos with extraordinary precision. It has provided the foundation for the most successful cosmological model in history. And it has given us this gift as well, this unsettled, unresolved, quietly insistent problem that will not let the model rest. The universe made the pattern in the plasma. The plasma froze the pattern in light. The light travelled for 13 billion years. Human beings built instruments cold enough and precise enough to read it, and what it said after all that was something is missing. Something about the universe's history or its composition or the laws that govern its behaviour is not yet in the equations. It seems that the universe has been preparing this particular message for a very long time. There is something almost tender in that when you hold it softly. The oldest light into the universe arriving at our instruments with a temperature so close to absolute zero that it registers as barely more than a tremor in the background of space. And embedded within that tremor, these ancient oscillations, these frozen sound waves from a plasma that cooled and cleared before the first star had ever burned. The universe's earliest legible words, written in temperature variations smaller than a millionth of a degree, containing within them a discrepancy that no one has yet explained. The message is patient. It has been crossing space for nearly 14 billion years. It can wait a while longer for someone to understand what it is saying. And in the quiet of a late hour, when the mind has loosened enough to let the large questions simply exist without needing to resolve them, there is a kind of companionship in that patience, in being part of the same moment as the travelling light, in resting alongside the open question. The ancient light knew something about the structure of space that took us thousands of years of science to begin to read. And even now, what the body quietly holds, its rhythms, its temperatures, its own ancient patterns, may be closer to the physics of the cosmos than it first appears. The body knows things the mind has not yet learned to say. It knows without being told when the room has grown too warm. It knows the difference between silence that is restful and silence that is tense. It adjusts its own chemistry in response to the quality of light, to the hour of the day, to the slow approach of sleep. All of it happening beneath the threshold of conscious awareness. All of it coordinated with a precision that no deliberate effort could improve upon. And here is what is remarkable. The mechanisms behind all of this are written in the same language as the universe we have been tracing through the dark. Not metaphorically, literally. The physics of heat and energy and oscillation that describes the early plasma, the acoustic waves frozen in the cosmic microwave background, the rhythmic pulsing of Cepheid stars, these are not separate phenomena from the rhythms of a living body. They are expressions of the same underlying mathematics operating at vastly different scales. The universe oscillates, and so do you. Begin with temperature. The human body maintains its core temperature within a remarkably narrow range, approximately 37 degrees Celsius, for most people, with natural variations of about half a degree above and below over the course of a 24-hour cycle. This variation follows a precise rhythm. Core temperature is lowest in the early morning hours just before waking. It rises gradually through the day, reaches a peak in the late afternoon, and then begins to decline in the evening. A decline that neuroscientists have observed is directly associated with the onset of sleepiness. This temperature rhythm is not incidental, it is causal. The cooling of the body's core is one of the primary physiological signals that initiates sleep. As the core cools, heat is redistributed to the extremities. The hands and feet warm slightly as blood vessels near the surface dilate, allowing heat to radiate outward. The familiar sensation of warm feet before sleep, the slight flush that sometimes accompanies the transition into drowsiness, these are the body's heat redistribution system doing exactly what it is designed to do. Researchers have found that environments which support this natural cooling, rooms that are slightly cool rather than warm bedding, that allows heat to dissipate rather than trapping it, significantly improve the quality of sleep onset and the depth of slow-wave sleep that follows. The body is trying to cool. The environment can either assist or resist. The timing of all of this is governed by a system of extraordinary elegance. Deep within the brain, in a small paired structure called the suprachiasmatic nucleus, located in the hypothalamus, just above the point where the optic nerves cross, sits the master clock of the human body. It is composed of approximately 20,000 neurons, and it generates a rhythmic electrical signal with a period of very close to 24 hours. Not exactly 24 hours, the endogenous period is typically slightly longer, around 24 hours and 15 minutes in most people, but close enough that daily light exposure provides the regular correction needed to keep it synchronized with the actual day. This clock and the cascade of hormonal and physiological signals it generates is the circadian rhythm. The word comes from the Latin meaning approximately a day, and the system it governs is far more comprehensive than most people realize. It regulates not just sleep and wakefulness, but body temperature, metabolism, immune function, hormone release, cell division rates, DNA, repair activity, the sensitivity of sensory systems, cognitive performance, mood. Essentially every physiological process in the body oscillates with this 24-hour rhythm, each tuned to its appropriate phase, each coordinated with the others through the master clock's timing signal. The discovery of how this clock works at the molecular level earned its researchers Jeffrey Hall, Michael Rosbash, and Michael Young the Nobel Prize in Physiology or Medicine in 2017. And what they found, working initially in fruit flies and later confirming in mammals, was a feedback loop of exquisite precision. Certain genes produce proteins that accumulate slowly over the course of several hours. When those proteins reach a sufficient concentration, they inhibit the very genes that produce them, causing their own production to slow. The proteins then gradually degrade. As their concentration falls, the inhibition lifts, and production begins again. The cycle repeats with a period of approximately 24 hours, a molecular oscillation, self-sustaining, self-correcting running, continuously in virtually every cell of the body simultaneously. Each cell carries its own clock. The liver cells run a clock, the lung cells run a clock, the cells of the skin and the gut and the kidneys all run their own versions of this molecular oscillation. They are coordinated by the master clock in the suprachiasmatic nucleus, which distributes timing signals through hormones and the nervous system, keeping the peripheral clocks synchronized with each other and with the external environment. What we understand so far suggests that disruptions to this synchronization, the kind produced by shift work, transmeridional travel, or the artificial light environments that characterize modern life, have measurable consequences for health across almost every physiological system studied. The body is not just a collection of functions, it is a temporally organized system, and the organization matters as much as the components. Light is the primary synchronizer. When light enters the eye, it is detected not only by the cone and rod cells that support ordinary vision, but by a third class of photoreceptor intrinsically photosensitive, retinal ganglion cells that project directly to the suprachiasmatic nucleus and communicate light information independently of conscious visual perception. These cells are particularly sensitive to short-wavelength light, the blue end of the spectrum around 480 nanometers, which is abundant in daylight and in the light emitted by most electronic screens. When these cells detect light, they send signals to the suprachiasmatic nucleus that shift the clock's phase. Morning light advances the clock. It signals that the day is beginning and helps align the internal rhythm with the external one. Evening light delays the clock. It signals that the day is not yet over and postpones the cascade of physiological changes that prepare the body for sleep. Evidence suggests that even relatively modest light exposure in the 2 hours before sleep, the kind produced by a phone or tablet at typical screen brightness, can delay the onset of the body's sleep preparation by 1 to 2 hours, reduce melatonin secretion, and shift the timing of deep sleep into a later portion of the night. The body is listening to the light, continuously updating its sense of what time it is, adjusting every physiological rhythm accordingly. Melatonin deserves its own moment here. It is often described as the sleep hormone, but this framing understates what it actually is. Melatonin is primarily a timing signal, a chemical broadcast from the pineal gland that communicates the onset of darkness to every tissue in the body. Its rise in the bloodstream, which typically begins 1 to 2 hours before habitual sleep onset, does not directly cause sleep. It signals that darkness has arrived and every clock in every cell adjusts its phase accordingly. It is less a sleep switch than a timestamp, a chemical annotation that marks the beginning of the biological night. The pineal gland, which produces melatonin, is one of the few brain structures that is not protected by the blood-brain barrier. This makes it unusually accessible to the bloodstream, which may be part of why it functions so effectively as a broadcast mechanism, releasing its signal into the circulation and allowing it to reach every tissue simultaneously. Scientists suggest that melatonin's role in coordinating biological timing is more ancient than its association with sleep. In simpler organisms, in fish and reptiles and birds, melatonin appears to coordinate seasonal responses, changes in reproductive timing, migration, hibernation based on the changing length of nights across the year. The pineal gland in many of these animals is light sensitive itself, detecting photoperiod directly through the skull. In mammals, that direct sensitivity has been lost, but the signaling role remains mediated now through the suprachiasmatic nucleus in the eyes. Sleep itself, when it arrives, is not the uniform state it appears from the outside. The brain cycles through distinct stages throughout the night, each with its own characteristic pattern of electrical activity, its own physiology, its own apparent function. The electroencephalogram, a measure of the brain's electrical activity through electrodes on the scalp, reveals these stages with clarity. In the lightest stages, brain waves are relatively fast and irregular. As sleep deepens, the waves slow and increase in amplitude, large synchronized oscillations called slow waves that sweep across the cortex in regular rhythms. In the deepest stage of non-rapid eye movement sleep, these slow waves dominate and the brain enters a state of metabolic quiet that is as deep as it will be during any period of unconsciousness short of anesthesia. Then periodically through the night, the brain shifts into a radically different state. Electrical activity becomes fast and irregular again, resembling the pattern of wakefulness. The muscles are paralyzed, actively inhibited by signals from the brainstem. The eyes move rapidly beneath closed lids. This is rapid eye movement sleep, and it is when the most vivid dreaming typically occurs. Researchers have found that these two states, slow-wave sleep and rapid eye movement sleep, appear to serve distinct biological functions. Slow-wave sleep is associated with physical restoration, with the release of growth hormone, with the clearance from the brain of metabolic waste products, including proteins associated with neurodegenerative disease, through a system of channels that expand during sleep and allow cerebrospinal fluid to flush through the brain's tissues. Rapid eye movement sleep appears to be important for emotional processing and for the consolidation of certain kinds of memory, particularly procedural memory, and the emotional content of experiences. The brain during sleep is not resting, it is working differently. The default mode network, a set of brain regions that become active during wakeful rest, during mind wandering, during the kind of unfocused awareness that precedes sleep, remains active in modified form during certain stages of sleep. It seems that the brain uses the withdrawal of external demands as an opportunity for a particular kind of internal processing, consolidating, sorting, pruning, integrating, running through the day's experiences with a different set of priorities than wakefulness allows. The hippocampus, which plays a central role in the formation of new memories, replays during sleep the patterns of neural activity that occurred during the previous waking period, sometimes in compressed form, sometimes at normal speed, sometimes in modified sequences that may help integrate new memories with existing knowledge. Neuroscientists have observed this replay directly by recording from hippocampal neurons in sleeping animals and recognizing the firing patterns from the animal's earlier experience. The mind, while it appears still, is actually doing some of its most important work. It may be that the oscillations of the sleeping brain, the slow waves sweeping across the cortex, the cycling between sleep stages, the replay and consolidation and clearing, are in some sense the body's version of what the early universe did in its plasma phase. A period of oscillation and settling, of patterns being established and preserved, of a system working through its initial conditions before the next phase begins. This is not a strict scientific analogy, but it is not entirely without basis either. The mathematics of oscillating systems, whether they are acoustic waves in a plasma, or electrical waves in a sleeping cortex, or the pulsing brightness of a Cepheid star, share deep structural similarities. Resonance feedback phase amplitude. These are the same concepts applied at vastly different scales, describing systems that have found their natural rhythms and are moving through them. The universe oscillated in its early plasma and froze those oscillations into the pattern of the cosmic microwave background. The brain oscillates in sleep and writes those oscillations into memory, into restored tissue, into a nervous system prepared for the next day. Both are forms of consolidation. Both are how a complex system processes what it has experienced and prepares for what comes next. The hour is late now. The room is quiet, or nearly so. Your core temperature has been falling gently for the past hour or more, the body already ahead of the conscious mind in its preparations, already redistributing its heat, already beginning to slow its metabolic activity in anticipation of what comes next. The melatonin has been rising in the bloodstream since the darkness settled in. The suprachiasmatic nucleus has updated its sense of time. Everything is already in motion. Everything was in motion long before this moment the biological rhythm set in place by the light of the day. The temperature of the room, the quiet accumulation of adenosine in the brain through the waking hours, the long, slow biological preparation for precisely this. It seems that the body has known all along that this moment was coming, and it has been getting ready. The same universe that encoded its early oscillations in the ancient light that left its patterns in the cosmic microwave background for billions of years also made the oscillating brain the cycling clock, the cooling body settling into rest. And in the space between those two scales, the cosmic and the cellular something has been quietly organizing itself all along. There is a question that lives at the very edge of science. Not at the edge in the sense of being far away or difficult to reach, but at the edge in the sense of being right here, immediately present, closer than any telescope could point. It is a question that every person who has ever lain awake in the dark has implicitly asked, without necessarily framing it in scientific terms. And it is a question that physics and neuroscience and philosophy have been circling from different directions for as long as careful human thought has existed. The question is simply this: what is it like to be aware? Not how awareness works mechanically. Not which neurons fire or which neurotransmitters are involved or which brain regions activate in response to which stimuli. Those questions have answers or partial answers, or answers that are improving with every generation of imaging technology. The question that remains is different. It is the question of the experience itself. The felt quality of seeing blue or hearing a note of music or sensing the particular weight of this moment, this quiet, this gentle drift between wakefulness and sleep. Scientists have a name for this. They call it the hard problem of consciousness. And it is in the assessment of many who have studied it carefully the deepest unsolved problem in all of science. The easy problems of consciousness, and they use the word easy advisedly, because none of them are simple, are the mechanistic ones. How does the brain integrate information from different senses into a unified perception? How does attention select some stimuli for processing while filtering others? How does the brain regulate its own states, shifting from alert wakefulness to relaxed drowsiness to deep sleep? These are difficult scientific questions, but they are in principle tractable. They can be approached with the standard tools of neuroscience recording, from neurons imaging, brain activity lesioning specific circuits and observing the effects, building computational models that replicate observed behaviors. Progress on these questions has been substantial. Neuroscientists have observed with increasing precision the neural correlates of attention, of perception, of memory retrieval and formation of emotional response. The machinery of the brain is being mapped with a resolution and completeness that would have seemed impossible a generation ago. But mapping the machinery does not answer the deeper question. Knowing exactly which neurons fire when you see the color red does not explain why seeing red feels like anything at all. The firing of neurons is a physical process, electrochemical signals propagating along axons, neurotransmitters, crossing synaptic gaps, ion channels, opening and closing. All of this is in principle describable in the same physical terms as any other process in the material world. And yet from this physical process, somehow, subjective experience arises, sensation, feeling, the inner quality of being present. How that happens, how matter organized in a particular way gives rise to experience, is what makes the hard problem hard. The philosopher David Chalmers, who gave the hard problem its name in 1995, framed it this way: even a complete physical description of the brain would leave something unexplained. You could know everything about the neural processing that occurs when a person sees a sunset, every photon detected, every signal transmitted, every cortical response, and still not know from that description alone what the sunset looks like to that person. The subjective character of the experience is not captured by the objective description of the process. This is not a gap that more neuroscience will automatically close. It is a conceptual gap, a place where the standard framework of physical science, which describes the world in terms of particles and fields and forces and information, seems to lack the vocabulary to address the question being asked. It may be that the framework needs to be extended. That consciousness is not something that can be derived from physics as it currently stands, but something that requires new concepts, new categories of description that do not yet exist in either physics or neuroscience. Some researchers have proposed that consciousness might be a fundamental feature of the universe, not something that emerges from complexity, but something that is present in some form wherever information is being processed. This view, sometimes called panpsychism in its philosophical form or integrated information theory in one of its scientific formulations, suggests that the capacity for experience is not unique to biological brains, that it is in some attenuated form a property of organized matter more generally. Integrated information theory, developed by the neuroscientist Giulio Tononi, attempts to make this idea mathematically precise. It proposes that consciousness corresponds to a quantity called phi, a measure of how much information a system generates as a whole above and beyond the information generated by its parts independently. A system with high phi1 whose parts are richly interconnected and interdependent has a high degree of integrated information, and therefore, according to the theory, a correspondingly rich experience. The human brain, with its approximately 86 billion neurons and roughly 100 trillion synaptic connections, has an extraordinarily high phi by any reasonable estimate. Simple systems, a thermostat, a calculator, a collection of independent components have phi values near zero. The theory predicts that these systems have little or no experience. Complex, highly integrated systems have high phi and correspondingly rich experience. One of the theory's predictions is that the level of phi changes across states of consciousness. In alert wakefulness, phi is high. In dreamless deep sleep, it drops significantly. Under general anesthesia, it drops further still. Researchers have found that measurements of integrated information using transcranial magnetic stimulation combined with electroencephalography do appear to track these states in a way that correlates with the presence or absence of conscious experience. The methodology is imperfect and the theory remains controversial, but it represents a serious attempt to build a scientific framework for the study of consciousness that goes beyond simply mapping neural correlates. Another framework approaches the problem from a different direction entirely. Global workspace theory, associated with the cognitive neuroscientist Bernard Baars, and later developed in neural terms by Stanislas Dehaene and Jean-Pierre Changeux, proposes that consciousness arises from a particular pattern of brain activity, a global broadcast. According to this view, the brain consists of many specialized modules processing information in parallel and largely independently. Most of this processing is unconscious. It happens, influences behavior, and concludes without ever reaching awareness. Consciousness occurs when information is selected and broadcast widely across the brain's networks, when a local process gains access to the global workspace and its contents become available to a wide range of cognitive systems simultaneously. The neural signature of this global broadcast has been studied extensively. It seems to involve a sudden late wave of neural activity occurring approximately 300 milliseconds after a stimulus in which frontal and parietal regions of the cortex light up simultaneously, the activity spreading from the initial sensory areas into a widespread network. This ignition, as it has been called, is reliably associated with the subjective report of having seen or heard something consciously. Without the ignition, stimuli can be processed and can influence behavior, but they're not reported as consciously perceived. Evidence suggests that during sleep, this global broadcast mechanism operates differently. In non-rapid eye movement sleep, the slow waves that dominate brain activity create a landscape in which global communication across cortical areas is periodically disrupted. Information can arrive, the brain continues to process sensory input during sleep, and familiar or meaningful stimuli can still elicit responses, but the global ignition that characterizes conscious perception is suppressed. The brain processes without fully broadcasting. The mind registers without fully knowing. What we understand so far suggests that consciousness is not a single thing, but a spectrum of states, each with its own neural signature, its own subjective quality, its own relationship to the machinery of the brain, the vivid wakefulness of a fully alert mind, the relaxed, loosely associative awareness of the period before sleep, the strange, internally generated reality of dreaming, the deep quiet of slow-wave sleep where experience, if it exists at all, is minimal and difficult to recall. Each of these is a different configuration of the same biological system producing a different quality of inner life. The transition between waking and sleep, the state you may be drifting toward right now, has its own name and its own distinctive phenomenology. It is called the hypnagogic state, from the Greek words for sleep and leading. In this state, the mind generates imagery spontaneously, brief, vivid, often fragmentary visual and auditory experiences that arise without narrative logic and dissolve equally quickly. The boundary between voluntary thought and involuntary experience becomes permeable. An idea arises. It is not quite chosen, not quite noticed. It simply appears, lingers for a moment, and is gone. Psychologists often note that this state is associated with a loosening of the default cognitive habits, the usual patterns of association and self-monitoring that structure waking thought. In the hypnagogic state, connections form more freely, analogies arise more readily, and the mind sometimes finds solutions to problems it has been working on without apparent effort. The composer Beethoven reportedly held a metal ball in his hand as he dozed in his chair, so that when sleep arrived and his grip relaxed, the falling ball would wake him, and he could capture whatever had been arising in the transitional state. The great unsolved question of consciousness connects in ways that are still being explored to the great unsolved questions of physics. Both involve something that appears from one angle to be well described by existing frameworks and then from another angle refuses to be. The Hubble tension is a number that doesn't fit. Consciousness is an experience that doesn't reduce. In both cases, the existing framework is not wrong exactly. It works extraordinarily well for most of what it addresses, but at these edges it runs out. It points towards something it cannot fully contain. Some physicists have speculated carefully without overclaiming that the relationship between consciousness and the physical world may not be entirely one-directional. The standard view is that physical processes produce mental states full stop. But the measurement problem in quantum mechanics, the question of what determines which of many possible outcomes of a quantum event is the one that actually occurs, has led some theorists to wonder whether the presence of an observer, or something like consciousness, plays a role in the collapse of quantum possibilities into definite realities. This remains genuinely speculative. Most physicists are skeptical that consciousness has anything to do with quantum measurement, but the fact that the question can be asked at all that the two deepest unsolved problems in science, the nature of the universe's fundamental laws and the nature of subjective experience, might somehow be related is itself remarkable. Two edges of the same unknown territory approached from different directions, possibly meeting somewhere in the dark. Tonight, in the particular quiet of this hour, your brain is doing something it does every night, something whose mechanisms are increasingly understood and whose deeper nature remains in the most fundamental sense mysterious. It is preparing to lose its ordinary continuity of self, to release the narrative thread it has been maintaining all day, to pass through the hypnagogic threshold into a state where experience, if it persists, operates by different rules, more associative, less controlled, stranger, and often more vivid than the careful logic of waking thought. This happens every night. It has happened every night of your life, and scientists are still exploring what it actually is. What consciousness is doing during that passage, what continues and what ceases, what the sleeping brain experiences in its deep, low oscillations, and what it simply processes without experiencing at all. The hard problem remains hard. The question of what it is like to be aware has not been answered by any instrument or any equation, And perhaps that is fitting for a night like this, a night spent tracing the edges of what is known, letting the unknown simply be present alongside the known without needing to close the distance. The universe does not know what it is like to be the universe. Or perhaps in some sense that no framework has yet described it does. The mind, it seems, has been keeping something still and patient all along, something that the deepest questions of physics and the quietest moments of the self have always shared without quite knowing it. Something in the body already knows how to be still, not the stillness of waiting, not the tense-held quality of a body bracing for something, but the other kind, the kind that comes when the day is genuinely finished, when the mind has released its grip on the afternoon's unresolved threads, when the breath has found its own natural depth without being asked. That stillness is not absence. It is a particular state physiologically distinct, measurable with its own signature in the nervous system, and its own relationship to the rhythms we have been tracing through the night. And what is remarkable is how far back that state goes, how ancient it is, how deeply written into the architecture of living things. Begin with the breath itself. At rest, the average adult breathes approximately 12 to 16 times per minute. Each breath is not a simple mechanical event. It is a finely coordinated process involving the diaphragm, the intercostal muscles, the smooth muscle of the airways, and a sophisticated neural control system located in the brainstem that regulates the timing and depth of each respiratory cycle. This system monitors the concentration of carbon dioxide in the blood, continuously adjusting the rate and depth of breathing in real time to maintain the precise chemical balance that the body's cells require. What researchers have found is that the respiratory system does not operate in isolation. It is deeply coupled to the cardiovascular system, to the nervous system's regulation of arousal, and to the brain's own electrical rhythms. Each inhalation is accompanied by a slight acceleration of the heart rate. Each exhalation brings a slight slowing. This rhythmic variation in heart rate synchronized with breathing is called respiratory sinus arrhythmia, and its magnitude is considered a marker of the nervous system's flexibility, its capacity to shift smoothly between states of activation and rest. The nerve that mediates this, coupling the vagus nerve, the longest cranial nerve in the body running from the brainstem down through the chest and into the abdomen, is one of the primary pathways through which the parasympathetic nervous system exerts its calming influence. When vagal tone is high, the heart's response to breathing is robust, and the body moves easily between engagement and rest. It seems that slow, deep, rhythmic breathing, the kind that happens naturally as sleep approaches, directly increases vagal activity, shifting the nervous system toward its rest and digest mode, slowing, the heart relaxing the vasculature, quieting the arousal systems of the brain. This is not a technique exactly, it is the body's own physiology running the program it was built to run whenever the conditions allow. The conditions that allow it have a name in neuroscience. The state of reduced arousal, of physical relaxation, of diminished cortical activation that characterizes the transition towards sleep involves a shift in the balance between two branches of the autonomic nervous system, the sympathetic branch which mobilizes the body for action, and the parasympathetic branch which restores it to equilibrium. During wakefulness, and particularly during stress, sympathetic activity predominates. Heart rate rises, blood pressure increases slightly. Glucose is mobilized, the pupils dilate, digestion slows, the immune system shifts its priorities. The body is configured for engagement with the environment, for responding, for reacting, for handling whatever the day brings. As evening arrives and the need for that readiness diminishes, the balance shifts. Parasympathetic activity increases. The heart slows. The blood vessels relax. Core temperature begins its nightly decline, the one that signals to every tissue in the body that the biological night has begun. Digestion resumes. The immune system, freed from the energetic demands of the stress response, turns its attention to the long-term work of maintenance and repair. The body, in other words, has a program for exactly this, for the end of the day, for the release of vigilance. And it has been running that program in essentially this form for hundreds of millions of years. The autonomic nervous system predates the cortex by an enormous margin of evolutionary time. The brain structures that regulate heart rate and breathing and digestion and the rest response are among the oldest in the vertebrate nervous system, present in fish, in amphibians, in reptiles, in every branch of the vertebrate tree. The newest structures, the prefrontal cortex, the regions that support language and abstract reasoning, and the particular quality of human self-awareness are recent additions layered over ancient foundations that were already fully functional long before anything like human thought existed. This means that the capacity for physiological rest, for the parasympathetic shift, for the slowing of the heart, for the cooling and quieting of the body is not a human invention. It is not a skill to be learned or a practice to be developed. It is an inheritance. Something the body already knows how to do, written into its architecture by hundreds of millions of years of evolution available every night, requiring only that the conditions be met and the permission given. The conditions are already met. The body has been preparing since the light changed. There is another rhythm worth dwelling with, one that operates not in the seconds of a breath or the minutes of a sleep transition, but across the longer arc of a single night. The cycles of sleep, the oscillation between slow-wave sleep and rapid eye movement sleep that repeats approximately every 90 minutes through the night, are themselves embedded in a larger rhythm called the ultradian rhythm. Ultradian means shorter than a day, and these 90-minute cycles appear not only in sleep but in waking as well. Researchers have found that even during wakefulness, the brain cycles through periods of higher and lower cortical arousal, on roughly 90-minute intervals, periods of relative alertness, alternating with periods of reduced performance, increased daydreaming, and physiological change that parallels the rest phase of the sleep cycle. This waking ultradian rhythm is sometimes called the basic rest activity cycle, and it appears to be a fundamental feature of mammalian neurobiology rather than a cultural artifact of schedules and routines. Animals without access to clocks or social cues still show these cycles. The brain seems to require periodic rest, not just at the scale of a day, but at the scale of an hour and a half. Brief windows of reduced arousal that serve as maintenance periods for the neural system supporting sustained attention and cognitive performance. What we understand so far suggests that the tiredness that arrives in the early afternoon, the post-lunch dip that many people experience, is not primarily caused by eating as is commonly assumed, but by the intersection of the circadian rhythm's natural trough with one of these ultradian rest phases. Two rhythms aligning in a way that produces a stronger signal than either would alone. The body is in this sense a timekeeper of extraordinary complexity. Not one clock, but many nested and overlapping, operating at different scales, each one synchronized with the others and with the external world through a web of chemical and electrical signals that is still being fully mapped. The second-to-second rhythms of heartbeat and breath, the 90-minute ultradian cycles of rest and activity, the 24-hour circadian cycle that governs the overall architecture of the day, the monthly rhythms that govern certain hormonal systems, the annual rhythms that subtly affect mood metabolism and the timing of biological processes in ways that studies indicate are more pervasive than most people realize. Each of these rhythms is in its own way a measurement, a continuous ongoing assessment of where the body is in time, what it needs, what it has recently done, what it should prepare for next. The body does not experience time as a neutral medium through which events happen. It participates in time actively through these nested oscillations. It is always in some sense measuring. This is where the personal and the cosmic touch. We have spent this night tracing the universe's own measurement problems, the tension between two ways of measuring the expansion rate. each internally consistent, each pointing to something the other cannot fully account for. The universe is also in its way a timekeeper. The expansion rate is a measure of cosmic time, of how the universe has changed since the beginning, of how the relationship between distance and recession velocity has evolved across 13 billion years of history. The Hubble tension is at its core a disagreement about that evolution, about whether the universe has been keeping the same time throughout its history, or whether something has shifted, some parameter changed, some new physics entered, that has caused the late universe to run at a slightly different pace than the early universe predicted it would. It may be that the universe, like the body, does not keep perfectly uniform time, that its clocks have drifted, or that what appeared to be a single clock is actually several each, measuring something slightly different, each accurate within its own domain, each disagreeing at the margins. The body's clocks drift too. They are reset daily by light and temperature and social cues. Without those resetting signals in the unchanging environment of a cave or a polar winter, the circadian clock runs slightly long, gaining or losing minutes each day, drifting gradually out of phase with the external world. The clock is real and it is accurate, but it needs the world to keep it calibrated. Perhaps the universe's expansion rate needs something similar. Some signal, some physical process, some force that has been operating across cosmic time and calibrating the expansion in ways our current models have not yet accounted for. The vagus nerve drifting through the body on its long descent from brainstem to abdomen carries signals in both directions, downward from the brain to the organs and upward from the organs to the brain. The majority of its fibers, perhaps 80%, carry information upward. The body is continuously reporting to the brain, not in language, not in anything like conscious communication, but in a constant stream of physiological data: gut motility, heart rate, lung inflation, the state of the immune system, the chemical composition of the blood. This information reaches the brainstem and the hypothalamus, and through them influences the higher cortical processes that constitute conscious thought and emotional experience. The feeling of calm or unease, of heaviness or lightness, of the particular quality of ease that comes with genuine physical relaxation. These are not purely mental events. They are the brain's interpretation of the body's ongoing self-report. The feeling of being at rest is the brain receiving signals from a resting body and generating the subjective experience that corresponds to that state. This is why physical conditions matter so much to psychological state. Why the temperature of the room, the softness of what you are lying on, the depth and ease of the breath are not incidental to the quality of the night ahead. The body is reporting and the brain is listening, and the quality of that report shapes the quality of experience. Somewhere in the nervous system, the signals are already shifting. The sympathetic activity that carried the day's demands is stepping back. The parasympathetic tone is rising quietly without fanfare. The heart rate has slowed by a few beats per minute in the last hour. The breathing has deepened slightly. The muscles, if you pay attention to them, have released some of the tension they hold during waking hours, the small unconscious contractions of readiness that the body maintains throughout the day, preparing for movement that may or may not come. Neuroscientists have observed that this progressive release of muscular tension during sleep onset is associated with a decrease in the activity of the reticular activating system, the brainstem network that maintains cortical arousal during wakefulness. As that system quiets, the tonic activity of the motor neurons decreases, and the muscles that have been subtly active all day finally release. There is a particular quality to that release when you notice it, when the attention is soft enough and the body quiet enough to feel the difference between held and let go. It happens in the jaw often, and in the shoulders, in the small muscles around the eyes, in the hands, the body releasing what it no longer needs to carry. The rhythms of the body and the rhythms of the universe are not in the end separate categories of phenomenon. They are the same physics expressing itself at different scales, oscillation and feedback and synchronization and drift from the molecular clocks in individual cells to the cosmic expansion rate that has been running since the first fraction of a second after the Big Bang. To be a living body is to participate in all of these rhythms simultaneously, to breathe at the frequency the brain stem sets, to sleep and wake on the schedule the circadian clock keeps, to age on the timescale that cellular biology allows, to exist for a brief interval within the larger expansion that carries every galaxy away from every other galaxy at a rate two measurements cannot quite agree on. All of it is happening at once, always. Most of it below the threshold of awareness, the vast coordinated machinery of the body, and the vast uncoordinated mystery of the cosmos both present in the same moment, both carrying you forward in their different ways. And in the space where that awareness softens, where the sharp edges of the day have finally rounded, where the body has done its settling and the mind its loosening, something remains that is neither thought nor sensation exactly, but something quieter than both. Perhaps it is simply the rhythm itself, still moving, still present. The way the universe keeps expanding even when no one is measuring it, the way the heart keeps beating even when no one is listening, continuous, unhurried, asking nothing. There is a word in Japanese ma that has no direct equivalent in English. It refers to the space between things, the pause between notes in a piece of music, the gap between two people in a conversation where something unspoken passes, the interval between one breath and the next. Ma is not emptiness exactly, it is not the absence of something. It is a presence in its own right, a kind of meaningful interval, a space that holds rather than divides. Scientists do not use this word, but the phenomena it describes appear throughout the natural world at every scale in ways that suggest the intervals between things carry as much information as the things themselves. Consider the synapse. Between any two neurons in the human brain there is a gap, a physical space roughly 20 nanometers across, so small it is visible only with electron microscopy, yet functionally essential to everything the nervous system does. When an electrical signal reaches the end of one neuron, it cannot simply leap across this gap. Instead, it triggers the release of chemical messengers, neurotransmitters, which diffuse across the synaptic cleft and bind to receptors on the receiving neuron, either exciting it towards firing or inhibiting it from doing so. Everything the brain does, every perception, every memory, every emotion, every thought, every moment of recognition or confusion or calm, passes through this gap. The entire complexity of human experience is mediated by the chemistry of spaces 20 nanometers wide, repeated across approximately 100 trillion synaptic connections, all of them communicating simultaneously in patterns of extraordinary intricacy. Neuroscientists have observed that the synapse is not a passive relay, it is dynamic adaptive structure. The strength of a synaptic connection changes with use, a process called synaptic plasticity that underlies learning and memory at the cellular level. Connections that are used frequently become stronger. Connections that are rarely used weaken and may eventually be pruned. The brain is continuously reshaping itself through the activity of these gaps, writing experience into its architecture one synapse at a time. During sleep, this reshaping accelerates. The synaptic homeostasis hypothesis, one of the leading frameworks for understanding why sleep is necessary, proposes that the purpose of slow-wave sleep in particular is to restore the balance of synaptic strength that has been disrupted by a day of learning and experience. Throughout waking hours, as new experiences are encoded and new connections formed, the overall level of synaptic strength in many brain circuits increases. This strengthening consumes energy and resources. It also, if left unchecked, would eventually saturate the system, making it harder to form new memories and harder to distinguish signal from noise. During deep sleep, researchers have found there is a systematic downscanning of synaptic strength across large regions of the cortex. The connections that were strengthened during the day are selectively weakened not randomly, but in a way that preserves the relative differences between them. The strong connections remain stronger than the weak ones, but the absolute levels are brought back toward a sustainable baseline. The brain clears space for the next day's learning while retaining the essential structure of what has been learned. This downscaling appears to be what the slow waves of deep sleep are actually doing mechanistically. The synchronized oscillations sweeping across the cortex are the electrical signature of this large-scale synaptic adjustment. Sleep is not just rest for the brain, it is active maintenance. A nightly recalibration of the very substrate on which thought and memory depend. There is a parallel here that arrives quietly without needing to be forced. The universe, as we have traced it throughout this night, also faces a kind of recalibration problem. The Hubble tension, that persistent unresolved gap between two measurements, suggests that the universe's own accounting does not quite add up. That the parameters describing the early cosmos and the parameters describing the late cosmos are not in perfect agreement. That something in the evolution of the universe over 13 billion years has shifted in a way the current model does not fully capture. Perhaps the universe, like the sleeping brain, has been recalibrating. Perhaps the expansion rate we measure today reflects not just the initial conditions of the Big Bang, but the accumulated effect of billions of years of adjustment, dark energy, fluctuating dark matter, interacting the geometry of space, responding to the matter, and energy distributed through it in ways that are still being worked out in the equations. This is not a scientific claim. It is an intuition loosely held offered in the spirit of the hour, the way a mind loosened by a late-night quiet will sometimes find connections that the daylight self would immediately scrutinize and probably set aside. But the intuition is not entirely without basis. The universe is a dynamical system. It evolves. Its parameters may not be as fixed as the simplest models assume, and something in its recent history may have shifted it slightly out of alignment with its own predicted trajectory. What we understand so far suggests that connection, the linking of one thing to another across a gap, is among the most fundamental processes in the natural world. At the atomic scale, chemical bonds form when electrons are shared between atoms. Connection through the quantum mechanical overlap of electron clouds, holding molecules together with energies that make chemistry and biology possible. At the cellular scale, synapses connect neurons, allowing signals to propagate through networks of extraordinary complexity. At the organismal scale, nervous systems connect sensory surfaces to motor outputs, integrating information from the environment into coordinated responses. At the social scale, language and gesture and shared attention connect individual minds into the distributed cognitive systems that make culture and science and everything built from collective human effort possible. And at the cosmic scale, gravity connects pulling matter together across the void, drawing galaxies into clusters, holding solar systems in their configurations, keeping the moon in its orbit around the Earth, and the Earth in its orbit around the Sun. Connection is not an incidental feature of the universe. It is one of its organizing principles. The universe tends toward relationship, toward the formation of structures that are more than the sum of their parts, toward the emergence of complexity from simple initial conditions through the patient action of forces that link things across gaps. The human brain is by some measures the most connected object in the known universe. Not in terms of the total number of connections, the cosmic web of filaments linking galaxy clusters contains more interactions than any brain could, but in terms of the density and variety of connection within a bounded system, the brain has no known rival. 86 billion neurons, each one potentially connected to thousands of others. The total number of synaptic connections is estimated at somewhere between 100 trillion and 1,000 trillion a number. so large it exceeds the number of stars in 1,000 Milky Way galaxies. And these connections are not static, they are constantly changing, strengthening and weakening, forming and dissolving, adjusting their sensitivity and their timing in response to the signals passing through them. The brain you have tonight is not quite the brain you had this morning. Experience has modified it subtly through the mechanisms of synaptic plasticity, and the sleep that is approaching will modify it further, consolidating some of what was learned, pruning some of what was redundant, resetting the overall balance so that the connections carry their signals with clarity rather than fatigue. You will be in some small but measurable way different in the morning, not in any way you would notice. But the synaptic landscape of the cortex will have shifted slightly overnight, and the thoughts that form across it will follow paths that have been quietly reorganized while you were not watching. Evidence suggests that this is also how scientific understanding advances, not through sudden illumination alone, but through the slow reorganization of conceptual connections, the gradual strengthening of associations that prove explanatory, and the weakening of those that do not, until a new pattern becomes visible that was implicit in the data all along but not yet legible. The Hubble tension has been accumulating evidence for more than a decade. The measurements have been refined, the alternative explanations have been tested, and one by one found insufficient. The pattern of a genuine discrepancy has been strengthening the connections between independent lines of evidence, all pointing in the same direction. At some point, no one can say exactly when the weight of that accumulated evidence will shift from anomaly to breakthrough, from something to be explained away to something that explains. This is what the history of physics suggests, at least. The persistent anomalies have tended eventually to be the most productive ones. The things that didn't fit were pointing somewhere important. It may be that the same is true of the gaps in personal experience, the things that don't resolve the questions that remain open, the feelings that don't have names. Not problems to be solved so much as invitations to expand the framework, to develop new vocabulary, to find that the gap itself was a form of information pointing towards something that needed a larger container before it could be held. The synapse is a gap that enables communication. The space between galaxies is a gap filled with dark energy driving the expansion. The pause between breaths is a gap where the autonomic nervous system quietly adjusts the balance. The interval between waking and sleep, that hypnagogic threshold we visited earlier, is a gap where the ordinary logic of the day releases and something more associative, more fluid, more openly curious takes its place. Gaps are not failures of connection, they are where connection happens. Psychologists often note that one of the most consistent findings in the study of human well-being is the importance of feeling connected to other people, to a sense of meaning, to something larger than the immediate concerns of the self. This finding appears across cultures, across age groups, across very different life circumstances. The particular form that connection takes varies enormously, but the underlying need is remarkably consistent. Scientists are still exploring why this should be, why a social mammal would develop such a strong dependency on felt connection that its absence produces measurable physiological and psychological effects, and its presence is associated with outcomes ranging from faster wound healing to lower cortisol levels to longer life expectancy. The mechanisms are multiple and not yet fully mapped, but the relationship between connection and well-being is among the most robustly documented findings in behavioral science. It seems that the body treats social disconnection as a threat, activating some of the same neural and hormonal systems that respond to physical danger, producing the heightened vigilance and disrupted sleep that characterize social pain. And it treats connection as a form of safety, allowing the nervous system to down-regulate its threat responses, to release its vigilance, to settle into the parasympathetic ease that supports rest and restoration. To feel accompanied even in the quiet of a late evening is not a small thing. It has a physiology. It has a measurable effect on the body's readiness to rest. The universe is connected in ways we are still discovering. The quantum entanglement of particles that have interacted and then separated a phenomenon Einstein called spooky action, at a distance in which the measurement of one particle's state instantaneously determines the correlated state of its partner. Regardless of the distance between them, suggests that connection at the quantum level operates outside the ordinary constraints of space. Two particles that have been entangled share something that persists across any distance. Not a signal, not a force, but a correlation written into the fabric of their joint quantum state. The mind quietly registers something in this, not a mystical claim, but a physical fact, strange enough on its own terms, without embellishment. The universe contains woven into its quantum mechanical foundations a form of connection that does not diminish with distance, that persists, that links the histories of particles across whatever space separates them. Everything in the observable universe was in the first moments of the Big Bang in contact with everything else. Every particle in your body shares a common origin with every particle in the most distant galaxy visible to any telescope. The separation that exists now, the hundreds of billions of light years between here and the edge of the observable universe, does not erase that shared history. It is simply what 13 billion years of expansion looks like. You are connected in the most literal physical sense to everything the universe contains. The hour has grown very late. The body has been settling for some time now, the breath slower, the muscles less insistent. The quality of thought softened from its daytime sharpness into something gentler and more receptive. The nervous system has been doing its quiet work throughout this evening, preparing for the transition that is always approaching, always almost here. What researchers have found in studying the moments just before sleep onset is that the brain's activity does not simply switch off. It transitions. The default mode network, that broad coalition of regions active during rest and self-referential thought, gradually hands over to patterns of activity associated with the first stage of sleep. The transition is not abrupt. It is gradual, like a tide coming in, the waking patterns retreating, the sleep patterns advancing, the two overlapping for a time, in a state that is neither fully one nor the other. In that overlap, the mind often does something it rarely does in full wakefulness. It simply receives, without agenda, without the pressure to evaluate or decide or respond. Thoughts arrive and depart without being pursued. Images form without being interpreted. The quality of awareness shifts from active to receptive, from a mind that goes out to meet the world to a mind that simply notices what arises. This is in its way a kind of homecoming, a return to a mode of awareness that preceded language and logic and all the elaborate structures of the waking self. Something older. Something that the brain returns to every night as reliably as the breath, as patiently as the heartbeat. The gaps between things, between neurons, between galaxies, between this breath and the next are not empty. They are where the quiet work happens, where connection forms, where the old patterns release and the new ones begin their slow assembly in the dark. And somewhere between the last conscious thought and the first dream, the universe continues its expansion, unhurried, unmeasured, for now, simply moving as it has always moved, carrying everything gently forward into whatever comes next. There is a concept in physics called entropy. Most people have encountered it in some form, the idea that systems tend toward disorder, that heat flows from warm to cold and not the other way, that a broken cup does not reassemble itself from the floor. Entropy is often described as a measure of disorder, but this framing, while intuitive, is not quite complete. More precisely, entropy is a measure of the number of ways a system can be arranged while still appearing the same from the outside. A gas dispersed through a room has higher entropy than the same gas compressed into one corner, not because it is more chaotic exactly, but because there are vastly more ways for the gas molecules to be distributed through the whole room than there are ways for them to all occupy one corner simultaneously. The second law of thermodynamics, one of the most fundamental statements in all of physics, says that in any isolated system entropy tends to increase over time. The total disorder of the universe measured in this precise statistical sense has been increasing since the moment of the Big Bang and will continue increasing for as long as the universe exists. This is not a pessimistic statement, it is simply a description of the direction of time. The Big Bang began in a state of extraordinarily low entropy. Not low in the sense of being simple, the conditions of the early universe were in many ways more extreme and more energetic than anything that exists today. But low in the sense that the matter and energy were distributed in a very particular, very constrained way. The universe began with an improbable smoothness, with density variations of only 1 part in 100,000 as encoded in the cosmic microwave background, and it has been exploring the vast space of possible configurations available to it ever since. Stars are a consequence of this exploration. When regions of gas collapse under gravity, they move locally to a lower entropy state, more organized, more concentrated, but the heat and light they radiate into the surrounding space more than compensates, increasing the entropy of the universe overall. Stars are in thermodynamic terms entropy-generating engines. They take the low-entropy fuel of hydrogen and convert it into the higher entropy products of helium and heavier elements and radiation, paying the universe's entropy tax with interest. Life is also a consequence of this exploration. Living organisms maintain their internal organization, their low local entropy, by consuming free energy from the environment and releasing higher entropy waste. A plant takes in low entropy sunlight and carbon dioxide and releases higher entropy heat and oxygen. An animal takes in low entropy food and releases higher entropy heat. Every metabolic process, every cellular activity, every heartbeat and breath is locally entropy reducing and globally entropy increasing, each living thing a small eddy of order in the larger flow toward disorder. This is the context in which everything we have traced tonight makes its fullest sense. The expansion of the universe, the Hubble tension, the dark energy, the mysterious acceleration is part of the universe's long journey toward higher entropy. As space expands, as galaxies recede beyond each other's event horizons, as stars burn out and black holes slowly evaporate through Hawking radiation over timescales almost incomprehensibly long, the universe moves steadily toward a state of maximum entropy, a state in which no more free energy is available, in which no more work can be done, in which the temperature everywhere has equalized at something vanishingly close to absolute zero. This endpoint, the heat death, is not imminent. It is separated from the present moment by a duration that dwarfs the current age of the universe by factors that require scientific notation to express. Their last black holes will not finish evaporating for approximately 10 raised to the power of 100 years. The protons that make up ordinary matter may decay on timescales of 10 raised to the power of 34 years. Compared to these durations, the 13.8 billion years the universe has existed so far is less than the blink of an eye. We are, cosmically speaking, still very early. And yet the arrow of time that points toward that distant equilibrium is the same arrow of time that governs everything happening right now. The breath moving in and out, the neurons firing and resting, the slow cooling of the body in the quiet of the night. All of it participates in the same fundamental directionality, the same statistical tendency toward the exploration of available states, the same gradual dissipation of the ordered energy that was wound up, so to speak, at the beginning. It seems that the experience of time passing, the felt sense of before and after, of course, preceding effect of memory reaching backward and anticipation reaching forward, is at its deepest level a consequence of this thermodynamic arrow. The reason we remember the past and not the future is that the past has higher entropy gradients, more information has been generated, more states have been explored, more records have been written into the physical world. The direction we call forward is the direction of increasing entropy. Time's arrow and entropy's arrow point the same way. Researchers have found this connection between thermodynamics and the experience of time to be one of the most profound and least fully resolved issues in theoretical physics. Why the universe began in such a low entropy state, why it started so ordered that billions of years of increasing entropy have still not brought it to equilibrium, is a question that sits at the boundary of cosmology and the philosophy of physics with no fully satisfying answer yet available. The dark energy that drives the expansion may itself be a thermodynamic phenomenon in some sense. The accelerating expansion is carrying the universe toward a configuration of ever lower density, ever greater volume, ever higher entropy in the cosmic sense. What we call dark energy may be at some level the universe's way of maximizing the entropy it can eventually reach, expanding the available volume, increasing the number of possible configurations, exploring more of the vast space of states that the laws of physics permit. Or it may be something else entirely, something that has no thermodynamic interpretation at the current level of understanding something that belongs to the new physics that the Hubble tension is quietly gesturing toward. It may be that the resolution of that tension will teach us something not just about the expansion rate, but about the nature of entropy itself, about why time has the direction it does, about why the universe began so ordered, about what it means for a physical system to evolve. These are not questions that will be answered tonight. They are not questions that will be answered soon. But they are present alive in the work of physicists and cosmologists and philosophers of physics who are right now, somewhere in the world, turning these ideas over in the particular way that minds turn over ideas that are almost but not quite within reach. What we understand so far suggests that the universe's drive toward equilibrium, its long patient movement toward maximum entropy, is not a tragedy. It is in a sense the condition that makes everything interesting possible in the meantime. The stars exist because the universe is not yet at equilibrium. Life exists because the stars are converting free energy into radiation, and life has found ways to intercept that flow and use it to maintain local order. Thought exists because nervous systems have evolved to use that local order, to model the environment with sufficient accuracy to navigate it. The complexity and richness of the present moment of galaxies and species and cultures and the particular texture of a late night spent in quiet thought is a consequence of the universe being far from equilibrium, of there being a long, long way still to go. And in that sense, the Hubble tension is perhaps a gift, an indication that the universe is stranger and more complex than the current models capture, that the path from the Big Bang to the heat death runs through territory that has not yet been fully mapped, that there are features of the cosmos that have been shaping the expansion for billions of years, operating just below the resolution of current understanding waiting to be resolved into clarity. The night is very deep now. The questions have been following their own slow orbits, from the measurement of distant galaxies to the nature of dark energy from the structure of the early universe, to the oscillations of the sleeping brain, from the connections between neurons to the connections between everything that has ever existed. Each topic opening onto another, not through urgency, but through a kind of natural adjacency. The way one thought in a quiet evening leads to another, and another not logically but associatively following the gentle current of wherever attention happens to drift. This is what the mind does when it is allowed to. When the demands of the day have stepped back and the pressure to arrive somewhere specific has lifted, it wanders softly, It finds connections that the directed thinking of waking hours might not find. It holds things gently together without needing them to resolve. Scientists suggest that this wandering mode, the default mode network operating without external task demands, is not wasted mental activity. It is a different kind of work. The brain consolidating, integrating, quietly assembling the larger patterns that will not be visible until some later moment when the pieces have been arranged in the right way. The universe too has been assembling. 13 billion years of gravity pulling matter together. Generations of forging elements and scattering them outward. Planets accreting from the debris. Chemistry organizing itself into molecules of increasing complexity. Biology emerging from that chemistry slowly over hundreds of millions of years, finding forms that could persist and reproduce, and eventually develop the capacity to ask questions about the process that produced them. All of it is still happening. The assembly is not complete. The universe has not yet reached the configuration it is heading toward. Somewhere in its future, a future so remote it exists only in mathematics, it will approach equilibrium. But that future is very far away. Right now, in this moment, the universe is still elaborating. Still building complexity from its initial conditions, still exploring the vast space of possible structures that the laws of physics allow. And you are part of that elaboration. The breath moves, slower now. The intervals between breaths slightly longer. The body has found its rhythm, the one it settles into when the day is truly finished, when there is nothing left to attend to and the weight of the body against what it rests on is simply weight, nothing more. The heart continues, steady, slower than it was this morning. The suprachiasmatic nucleus has long since registered the darkness and set its signals in motion. The melatonin has been rising for hours. The slow waves are not far now, those great sweeping oscillations across the cortex clearing and resetting, consolidating what was learned, releasing what was not needed. The brain preparing itself in its patient nightly way for another day of encounter with the world. Somewhere a telescope is open to the sky. Mirrors collecting photons that left their source before the Earth existed. Detectors cooling to the temperatures close to absolute zero waiting for a signal. A measurement being made or prepared for or analysed in the quiet hours when the day's noise has died down, and the data can be examined with clear attention. The Hubble tension remains. The gap between two careful measurements of the same universe persists patient and unresolved as it has persisted for years, and will persist until the right question is asked in the right way with the right instrument at the right moment. The universe is not in a hurry. It has been carrying this particular mystery for billions of years already. A few more will not trouble it. The questions rest now. Not abandoned, not forgotten. Simply set down the way you set down something you've been carrying for a long time, not because you are done with it, but because the hands need to be empty for a while. The galaxies continue their recession, each one moving away from every other one, not through any will or direction, but because the space between them is still quietly, gently growing. The ancient light still travels. The dark matter passes through as it always has, silent, indifferent, present, and the body which is made of everything the stars have ever forged and scattered and gathered again settles further into the dark. The breath, a little slower, the thought that was forming gone before it arrived. Something like warmth, something like distance, the room, still. The universe very large, very quiet, still expanding into whatever it is expanding into, the question that has no answer, yet the measurement that doesn't quite agree with itself, the number that has been waiting patiently in the dark, still there. You don't need to hold it. It holds itself, the way it always has. The way the night holds everything without effort, without asking anything in return. Just open, just this.